satellite, Diwata 1, and the recently launched Cube satellite, Maya 1, kung nakita nyo dun sa booth ng DOST-ASTI and ng PhilMicrosat program sa baba, and the development of our second microsatellite, the Diwata 2. So, to get things going,
Yes. So we will be introducing our first speaker for the day. So before that pala, para sa mga students na nandito, the goal of this student forum is actually to give you guys an idea on what the R&D initiative.
So yun yung kanina kasi hindi siya naka-scale. So ito yung scale ng ano. So yung Earth, tapos low Earth orbit is about 180 to 2,000 kilometers. Tapos yung mid-Earth ay 2,000 to 35,700. 780. Tapos yun yung moon all the way out there. Tapos same na lang, to scale. So yung, kita nyo ba yung colors? Ito yung Earth. Yung dashed line na reds, dun yung International Space Station. So actually, it's really low. And then yung cyan, yun yung low Earth orbit, medium Earth. Tapos. So, ito lang yung relationship ng speed sa yung orbit. So, parang habang bumababa siya, bumibilis, ay, hindi kita. So, bumibilis yung speeds ng satellite as you go lower to the Earth kasi hinihila siya ng gravity. Tapos ito naman, yung next classification is you can also classify their orbits by yung shape. So, yung circular orbits, tapos yung E. Nag-geometry naman kayo nung dumating na ba kayo doon. So, E, eccentricity. So, yung deviation niya from the circle. So, a perfect circle has an eccentricity of 0. Tapos, as it becomes more eccentric, tumataas yung ano. Same lang yun. Tapos, yung next category naman ay you can categorize the orbits by yung ano niya, inclination. Yung inclination lang ay yung angle ng orbit niya from the equatorial plane. So, based on that definition, may 3 major categories ng satellite orbits. So, yung polar plane, so yung orbit mo ay it will go north-south. Equatorial plane, kung aligned siya sa equator. Tapos yung inclined, yung ano, yung in between those two. Tapos yung last na classification ng orbit ay yung sa synchronicity. So I think it's better illustrated. So for example, itong isang type ay yung Sunsynchronous. So yung satellite, special type siya nung polar orbit. So north-south siya. Tapos yung orbit niya is such that it goes around the Earth, tapos dumadaan siya sa isang spot sa Earth at the same time each day. So kung makikita nyo, pag nag-loop siya, di ba parang itong dark spot na to, yun yung day-night terminator. So diba, gumagalaw siya, pero parang hinahabol niya yung ano, but they never quite meet. So useful siya for monitoring kasi you want something na regular, like dadaan ka ngayon at 10 a.m., tapos the next day, 10 a.m. ulit. So pareho yung lighting conditions. Ayun. So yung isa naman yung geosynchronous. So umiikot pa rin siya pero sumasabay siya sa rotation ng Earth. So from the Earth, it's as if hindi siya gumagalaw. So kung may cable kayo sa bahay, yung I think signal ba yun? Yung may satellite dish. Di ba kayo nagtataka ba't naka-point lang siya in one spot? So gumagalaw yung satellite, pero sa perspective natin, sumasabay kasi siya sa ikot ng Earth. So, fixed point lang siya. And then, punta na tayo sa applications. Malapit na tayo matapos. So yun. Ito yung applications ng mga satellites. May astronomical satellites, communication satellites, navigation, space stations, saka weather at Earth observation. So, we'll go through them one by one. So, anyone know what that is? Yung satellite na yan. And Hubble, tama. Hubble Space Telescope. So yung satellite na yan, yung astronomical satellites, yung sensors nila naka-face outward, hindi siya naka-face sa Earth. So ano siya for observation ng heavenly bodies. The next one ay yung communication satellites, yung na-mention ko kanina, yung sa signal. Ang ginagawa nila, nagbabounce sila ng signals. For example, may nagbo-broadcast dito, curve kasi yung Earth at kailangan ng line of sight for broadcasting. So yung ginagawa niya, nagbabounce siya. So yun, actually ito ay, I think this is ABS-2, if familiar ka. I mean, Agila 2. Have you heard of Agila? Kasi before Diwata, we actually have our own satellites, Agila 1 and Agila 2, but hindi natin siya ginawa. We bought them, so yung Diwata yung first na we did ourselves. So communication satellite siya, tapos yung space station, na-discuss na natin kanina. Yung, right now, we have 2 in space, yung International Space Station, at may isa sa Chinese na space station. I forgot the name, sorry. And then we have weather satellites. So yung weather satellites, kung naalala niyo yung previous na discussions, siya ay is used to monitor the weather. So usually hindi siya geostationary sila kasi dapat naka-monitor ka at the same spot. Kasi nga 'di ba, yung definition ng weather ay changes sa atmospheric at short-term periods, 'di ba? Yung climate, yung long-term. So kailangan nandun siya all the time para makita niya yung development ng storms, etc. Tapos ito, wait, okay, hindi ka na-discuss yan. Yung importante pala, hindi ko nalagyan ng slide. Yung navigation sa...
Para sa inyo guys, is it cold or hot in space? Sino? Ano daw? Cold? Cold. So, cold yung sabi niya. Ikaw, kuya. Both hot and cold. Ayun. So, sinong tama? Si kuya number 1 or si kuya number 2? Sino yung nagsabing kuya number 2? Kuya number 2, wala? Kuya number 1. So, hati yung natin, yung audience natin. So, the answer is it's both cold and hot. So, when an object is facing or exposed to the sun, then mainit yung object na yun. Pag nasa likod siya ng Earth, hindi siya nakikita ni sun, then malamig. The next is yung drawings. Ayun, lumabas. Technical drawings. So you prepare this kind of drawings. So CAD, 3D models, and then you give these drawings, you check it. You do these drawings, then you check it if nagmamatch ba lahat or hindi. So, maniniwala ba kayo na when the team made Diwata 1, it started up like this one? So, cardboard lang. So, the team did this so that we would know saan ilalagay yung component na to, kung kasya ba yung lahat ng components na balak namin ilagay sa satellite o hindi. So, it all starts with a sort of mock-up. And then, it turned out this way in the 3D model. So after you finish the modeling of the drawings of the satellite, ang next step is yung simulation. So this is an example of a snapshot ng vibration simulation. So what we did here is gumawa kami ng model, vibration model, and then kung nakikita nyo tong red arrows dito, ito yung forces na nag-a-act dun sa model na yon. So kuwari, ang model na to, in this model, naka-attach yung satellite in these areas, so kaya andun yung red marks, and then we propagate those forces into the dun sa model na ginawa. Another is a thermal model. So, ibang model na naman siya. And then, we let this model rotate sa Earth. And then, we get this kind of results. So, after ng modeling, simulations, we make an structural model. Ito. So, mga dummy weights pa lang ang loob ng satellite mo. And we also make an engineering model. So, these models are the one tested sa vibration shaker and sa thermal vacuum chamber. So sila yung, in a way, binubugbog sa tests. So when we need to iterate, si kuwari, may nakita kaming problem, we need to change this and that. So we do those iterations dito sa models na to. So like I mentioned, you do some tests using those models. So yun. So pag nasa loob ka ng rocket, parang ganito yung mafe-feel mo. Shaking. Yan. So, pa-play na lang po ng video. So this is an actual video of the satellite tested in a shaker. So meron lang tayong idea how harsh the environment is inside a rocket. Kasi feel ko hindi tayo solve kay ate na nagsishake lang siya. And so this is an EM, engineering model of the Diwata 2 tested in the shaker. Ayun. Shaker. Shake it. So the next test is the thermal vacuum chamber. So this is what a chamber looks like, a small chamber looks like. So siguro if we watch videos of NASA or ESA or other space agencies, meron sila yung nakadikit na talaga sa floor, ganong type ng chambers. Pero since we are just we have a small satellite where we're testing a small satellite, so kasya na siya using in a 1,000 millimeter diameter na chamber. And then what we do is we close this door, may door yan, ko-close namin yan, we seal it, baba yung pressure until 1 to the negative 5 pascals, and then we lower down the temperature using liquid nitrogen. Tapos, when it reaches the certain temperature, say around negative 20 degrees Celsius, we test the components if it's working. So this is a picture taken by Diwata inside the chamber. So may pinoint na kaming light para makita if successful or not yung pag-test namin. And lastly, we also did a deployable test. Yeah, deployment test pala. And to check whether our deployment mechanisms work. So, as you know, merong deployable solar panels and antennas si Diwata 2 kung nakapunta na sa baba and na-explain na ng mga colleagues ko dun yung features ni Diwata 2. So, meron siyang deployable solar panels and antennas. So, we also try to do that test inside the thermal vacuum test chamber. So, other tests, antenna pattern test, and radiation test. So, in space, harsh radiation yung na-experience ng component, so pwede silang masira, tinatawag na single event upset. So when that happens, pwedeng hindi na gumana yung component totally or madamage siya for the whole So ma-affect niya yung performance ng satellite mo. So what we do is we test all those components in a radiation facility. So after all those tests, we start and we verify that nothing is critical, walang nangyayaring masama with the components. We now start building the flight model. So ito na yung flight model ni Diwata 1. And we do some final checks in a satellite setup. So say we dump commands in the satellite and see if it performs well and check kung okay ba yung response niya just on the ground. And then after nyan, ready na for delivery yung satellite mo. So that's all. Thank you.
Grabe, Joe, ang process of building a satellite.
Napaka-busisi.
Napakahaba pala. Siyempre, pag minadali mo, yung lilipad yun.
Thank you very much, Delbert, for that very wonderful presentation. Jervic, before we go on to the next speaker, kailangan nating ipa-realize sa mga high school students na nandito that the speakers that we have today are the actual engineers and scientists that worked on these satellites. It's the first Filipino satellites, Filipino-made satellites natin. And just maybe 10 to 15 years ago, they were just like them.
Oo, hindi nanonood sa National Science and Technology Week na forum, pero...
And lang.
So,
2023.
one of you guys will, hindi perhaps will make one of our satellites kung baka mag-move on na tayo into bigger and better and, more progressive satellites.
Yes, because this is just the start of the Philippine space program. So maybe when you guys come to, for your further studies, like in college or in your masters, baka kayo na rin yung magpe-present ng ganito to the younger generation.
Ngayon pa nga lang, parang dami na nilang alam tungkol sa satellite Kasi si Sir Del Burge, talagang ninalog yung tayong lahat dun sa satellite.
Also, wag kayong mag-alala, snacks will be served in a short while. And for everyone who has questions, mamaya po, magkakaroon tayo ng open forum. All of the speakers will be in front and you could get to ask them your questions. And anybody who asks a question, yung maganda na question, will get a free shirt from Phil Microsats.
Napakagandang shirt na yan.
All right, so from 50 kilogram satellites, 50 kilos ka ba?
Ay,
From 50 kilogram satellites, we now go on to the smaller satellites, those that can fit in the palm of your hand. So alam na ba nila yung Maya 1?
I guess kung nakapunta na kayo sa baba, no? So, explore pa natin si Maya 1.
So nakita nyo yung model ng Maya 1, yung replica, dun sa booth ng Phil Microsat. Sino na nakapunta doon?
Ayan, sila. O, di ba, kasya siya sa kamay niyo kung malaki yung kamay niyo.
There's satellites that can fit in the palm of your hand. So the next speaker is Mrs. Mary Ann Constante of the Phil Microsat Project 1. And she will give us an overview of nano satellites and cube satellites. So she is the acting manager of the Phil Microsat technical team. And she also works on the amateur radio payload for Diwata 2 and the ground sensor terminal for the Birds 2 project. So lahat po ng satellites na naka-display sa baba ay she had a hand in creating. Oh. Hinawakan niya yun. Nabasbasan niya yung lahat ng satellites dun sa baba. So she also helped develop the course on space technology in UP Electrical and Electronics Engineering Institute. So maybe some of you guys might be in that program in the future. And she finished her undergraduate degree in Electronics and Communications Engineering at UP Diliman. So everybody please welcome Mrs. Mary Ann Constante.
Hello. Correct ko lang si Miss Jo kanina, yung 10 to 15 years mali yata yun, kasi parang last year lang yun. Anyway, una sa lahat, good afternoon and thank you for coming here. Kahit na hashtag wala yatang pasok sa ibang school dahil merong hashtag in the IPH, di ba? Go. Okay, so I was asked to do a presentation on CubeSats. But more than that, actually, I'd like to talk more on whether these CubeSats are just another space junk. Lipat ako dito kasi ang taas eh. Hindi ata ako kita. Yan. So, marami yata sa inyo nakapunta na dun sa booth sa baba, no? So, nakita na ninyo yung CubeSat, yung Maya 1, yung replica. But still, since ina-assume ko kasi marami sa inyo hindi pa familiar sa CubeSat. So, may Wikipedia definition lang ako dito, which is, CubeSat is a type of miniaturized satellite or nanosatellite that is made up of multiples of 10 by 10 by 10 centimeters cubic units, and each unit has a maximum of 1.33 kilograms. So, just to illustrate, nakita nyo na rin ito kanina siguro. Ito yung CubeSat, 1U CubeSat, which is yung Maya 1. Just to put that to perspective, this is me holding that CubeSat. So medyo yabang lang yan. Joke. Okay, so you can imagine that CubeSat to be this big and my face to be that big. Rock on. Okay, and then, hindi magandang comparison, di ba? So nanghiram ako ng iPhone X and added it there. So ganyan kalaki yung iPhone X. So you can imagine yung iPhone X or yung normal phones ninyo, mas malaki pa sa isang 1U CubeSat. Okay. And next, yung CubeSat, it started as a reference design proposed by Professor Jordi and Professor Bob Twiggs of Cal Poly and Stanford University. And that CubeSat reference design in 1999 later on developed into the standard. So itong standard na to, nini-specify niya yung mga mechanical requirements, electrical, operational, and testing requirements, which is mostly same procedure as yung na-discuss kanina ni Delberge. Hey, so another yabang. That guy here is Professor Jordi in one of his seminars. So it's actually a great pleasure to be standing beside that living legend. Hey. Now, kanina, di ba alam natin yung CubeSat kasing laki lang ng kamay natin eh. And you might think that with that small size comes small responsibility, or you can say small capability. But then again, if you will look at how many CubeSats or nanosatellites are launched over year, you will see that in 2018, there are over 419 satellites that are planned for launch on 2018. And now looking at how many satellites are there around the globe, around the Earth, baka mapapaisip kayo, gosh, I'm just adding junks in space, di ba? Or not. Hey, so I'd like to jump to isa sa mga sinabi ni Professor Jordi nung isang seminar niya, which is, to maximize the benefits from satellite technology, you need people who fully understand a satellite's capability and can apply them to solve local problems. So if you will dissect that statement, basically there are two requirements to maximize space technology. And the first one are people who knows the problem. So ano to? Mga problems na very localized or very close to our heart. Kasi usually yung mga malalaking bansa, hindi sila nagkikare or pwedeng hindi sila aware na merong mga areas, for example, in Aurora, na walang GSM signal. And syempre, mas lalong, wala silang pake kung walang wifi sa bahay ninyo. Diba? Hey, so sino bang may alam ng problem sa Philippines? Of course, the President and his cabinet. Senators, congressmen, mayors, councilors, barangay captain, but most importantly, you guys. Tayo, alam natin, di ba? Now, people who solves the problem. This is the other requirement mentioned in Professor Jordi's seminar. But then there is one challenge for new space players, which is the space perception. So for a country like Philippines, we normally think that space is difficult. It is expensive, and it is only for few people. And then CubeSats entered. Hey. So CubeSats, they became a training platform to create people who can solve problems because they follow the same development stage of normal satellites. So it provides a great training potential to its students. So the training potential is very high because it will require not only field expertise. So kung kunwari mechanical engineer ka, dapat alam na alam mo yung mechanical engineering side. Yung pag-electrical engineer ka, dapat alam na alam mo rin yung mga electronics components. But more than field expertise, you also need to know systems level development. Because we need to integrate or mate or merge various fields, electrical, mechanical, science, and so on. And apart from that, you need to comply to safety requirements and tests. So nakita nyo kanina, di ba, kung gaano karami yung prosesong dinadaanan ng satellite development from design, development, and testing. And it doesn't end with developing satellites. Of course, you need to, ang tawag dito, mag-meet with policy requirements and, of course, document all that's being done. And once the satellite is launched, you need to operate it. Hey. And then, nagbago yung phone. Most importantly, in space, once the satellite is there, you cannot do any maintenance or repairs. So basically, you need high-quality design and manufacturing. Hey, so the Kyushu Institute of Technology in Japan started the BIRDS project, which aims to capacitate non-space players nations to learn how to develop their own satellites. And the Philippines joined that project, which is the BIRDS 2 program. So the BIRDS 2 program and yung Maya 1, which is yung sa Philippines, was co-developed with Malaysia and Bhutan. So sila tong nandito, Malaysia and Bhutan. And these are the engineers that developed these CubeSats. Okay, so just to give you an overview of how a CubeSat is developed, na-discuss na kanina ni Delbert yung details noon. But basically, it follows the same stages of development of regular satellites. So you start with mission idea and development because you need to make sure that the satellite will be useful. So that's why you have to consult stakeholders kung ano ba yung mga kailangan nilang problems na i-solve. And then you proceed with the engineering development stage. So yung prototyping, testing if it will work, and subjecting it to several testing na binanggit na ni Delbert kanina. So, ito yung breadboard model ng BIRDS 2, and then ito yung engineering model ng BIRDS 2, and these are the tests performed on this satellite. So yung engineering model, basically, pwede na siyang mag-pass as flight model. Pero engineering models are tested with margins or tested at a more rigorous environment than the flight model. Okay, so at times, this engineering model becomes the flight model as well. So parang siya nagiging engineering/flight model. Okay, so pag yung satellite ay nakapasa na sa mga test na to, that's when the flight model is developed. So these are some pictures from the assembly of the flight model of BIRDS 2. Okay. So what can CubeSats do? Or basically, ano ba yung mga normal missions ng isang CubeSat? Isa sa mga primary missions aside from capacity building is technology demonstration. So mostly CubeSats are used to demonstrate that a commercial off-the-shelf part can work in space. And that helps us build a database of parts that can be used, which is critical in sustaining space technology in one country. Kasi kapag bumili ka ng mga space-grade parts, normally sobrang mahal nila and sobrang hirap nilang bilhin kasi you have to go through several import requirements. So, kung gusto mong mag-proceed with satellite development or gusto mong sustain yung ganong activity in your country, you need to be familiar with what components can you use for space applications. And normally, you do not fly untested parts in expensive expensive satellites. You do them in cube satellites. Okay, and another are scientific experiments. So scientific experiments allow us to gather information useful to community and other developers. Like for example, performance detection due to radiation. And CubeSats can also be used for providing services. This one here, this amateur radio is an already well-established technology. And in fact, this is already used in supporting communications kapag nagkakaroon ng mga disasters. So kung naalala niyo nung Yolanda, maraming mga publications noon na yung ARRL, tumulong sila sa pag-provide ng communications during that time para sabihin na, hey, buhay pa ako sa mga relatives sila na nasa ibang lugar. Okay. And then this store and forward is a system wherein you can deploy remote sensors in remote areas. And when the satellite passes through this area, it can collect the data from the sensors. And then when this satellite moves and reaches a ground station, it can dump its data to that ground station. So how are these technologies be applicable to a country like the Philippines? Okay. First, I mentioned already as an alternative communications kapag nagda-down yung mga regular infrastructures, which is laging nangyayari kapag nagkakaroon ng mga calamities. And then, collecting information that can be useful for early warning. Like for example, data from landslide sensors or data that will be useful to predict or basically warn people that there's an incoming flash floods. It can also be used for health monitoring. So you can collect patients' information from very remote areas, and then they can be sent to a satellite, and then the satellite will dump those data to the ground station where the data can be used or accessed by the doctors in the cities. So actually, this one here is one of the projects of Department of Science and Technology. they deployed basically tools in remote areas, and that collects patients' information. But one limitation is that, of course, you require mechanism to transmit that data to doctors. So basically, kapag wala talagang access yung isang lugar, mahirap gawin tong mga to. And another thing is for tracking, like for wildlife tracking or for fish vessel tracking. Okay. So this is just a timeline of different satellite missions over time. So you can see here from simple test of cameras or testing of parts and basic establishment of communication with the satellite. Basically, just trying to make a CubeSat work in space, up to demonstrating several technologies, new technologies like store and forward, or 3D printing in space. And in fact, they are now planning to build, to launch a CubeSat that is fully built by high school students, just like you guys. And this timeline does not show over 301 new CubeSats. So lahat to 1 new CubeSats. There's even PhoneSat in 2013. May series to 1 to 2.5, which demonstrates commercial smartphone in space. Okay. So I don't want to raise eyebrows in this slide, but just to make some comparison versus a geostationary satellite. So for example, we want to accomplish a mission that will provide communications to remote areas. So of course, the geostationary satellite can provide communication for 24 hours versus CubeSats. Assuming 50 CubeSats, you can establish communication for 24 hours with approximately 15 minutes downtime per hour. So, and the cost of this development and launch are roughly these figures, and then the insurance and operating cost, and then the lifetime. So the total unit cost for a 1 unit CubeSat is 12 million pesos versus the cost of a geostationary satellite, which is 16.25 billion pesos. Now, if we want to match the capabilities of this geostationary satellite, we'll multiply this by 50. So basically, you need 9 billion pesos for 50 units of 1 new CubeSat for 15 years versus the 16.25 billion peso of the geostationary satellite. Okay. So, now, pwede mo kasing sabihin, uy, konti lang naman pala yung difference. Tapos may geostationary na ako, mas maraming capability. But then again, doon papasok yung point na in-establish natin kanina, na you need people who knows the problem. And ano ba yung current na problem natin sa Pilipinas? Maybe we don't need yet a geostationary satellite developed locally. Maybe we need to provide communications to remote areas. So maybe not yet a geostationary at this point because we want to solve immediate problems, and that is information poverty. Okay. And another advantage of these CubeSats are that it wouldn't hurt much if one of them fails. Kasi ang dami nga nila, di ba? Unlike if a geostationary satellite, that 16 billion peso satellite that we developed, if it fails, it's bye-bye satellite, di ba? And then, the cost here of CubeSat is actually not a mass production cost, and some components are purchased abroad. So you can lower down the cost even more if the satellite is developed locally, and if you have test facilities to test that satellite. And you can even include experiments and cost parts for your CubeSat versus a geostationary, where only reliable parts can be used. Okay. So now, CubeSats, one good thing about them is that they use non-traditional risk-taking development and management approaches with the aim to provide value at low cost and on-time delivery. So basically, it's okay to take risks as long as they are understood and managed. And the main goal is to be able to deliver value to stakeholders within a short timeline. And this philosophy is actually called the lean satellite development philosophy, although this is also applicable to other satellite classes. Okay. So now, going back to our question earlier on whether CubeSats are just another space junk, I can't tell you a downright yes, because like what I've mentioned, there are two requirements to be able to maximize the benefits from space technology. And number one are people who understands the problem, and number two are people who can apply technologies to solve those problems. And hopefully, these people would later on be you guys. Okay? And that ends my presentation. Thank you.
Thank you very much, Miss Constante. So, ayun. So, siguro, to summarize the whole presentation, it's not about the size, it's about the performance, di ba? So, maybe what we need now is to solve our immediate problems and using, a relatively lower costs na technology. So, to continue with our program while we enjoy our afternoon snacks. So from the development of the satellite, we will now learn how Diwata takes its photos and how we can use these images. So before we move on to our next speaker, we would like to acknowledge the presence of the Acting Director of the DOST-Advanced Science and Technology Institute, Dr. Joel Joseph S. Marciano Jr. So our next speaker is Mr. Francisco Miguel Felicio. He is one of the PhilMicrosat's research associates. He assigns operational and research-related tasks of image acquisition and downloads for Diwata 1. He is currently taking his master's in environmental science at the University of the Philippines, Diliman. And he finished his undergraduate degree in applied physics in UP Los Baños. So help us welcome Mr. Miko Felicio.
Hello, hello. Okay. Hi, good afternoon. Ako nga pala si Miko. Sino yung mga nag-attend kaninang umaga? Meron ba? Higher, please, para makita ko. Okay, so marami rin palang bumalik. That's good. Okay, so this afternoon, I will be talking about Diwata 1's operation, how it's operated. We want to know how we operate Diwata 1 in a day-to-day basis and why we do so. Okay, so first, next, okay. A small background, so Diwata 1, as you've already heard, is a 50-kilogram microsatellite. It was deployed from the International Space Station last April 27, 2016, and it has a 55 by 55 by 35 centimeter dimension. So if you've been to the booth, it's roughly the size of a CPU, an old CPU, and it has an altitude of 400 kilometers. So 400 kilometers, that's equivalent to traveling EDSA 20 times, or as high as or 1,333 times the height of the Eiffel Tower. Okay, so at 400 kilometers, can you see? So this is Diwata 1. This is a little simulation I made. So this is Diwata 1, the little red dot, and this red line is the orbit. So at 400 kilometers, Diwata 1 orbits the Earth at approximately 90 minutes per revolution. And it travels at a speed of 7.4 kilometers per second. So that's 90 times the speed of a bullet train. So that's really fast. So it's per second, not per hour. Okay. So next, I would like to show you this image. This is actually an image of some of Diwata 1's cameras. So Diwata 1 actually takes pictures of the Philippines. So it's what it's meant to do. So it takes pictures of different wavelengths of light. So it takes images from blue to green to yellow to red, and some near infrared. So later on, probably the next presenter will discuss this some more. So here's a sample image of a place in the Philippines, colored in blue. Another one taken using a green image, and then another one using red. So it's black and white. Well, the computer doesn't know what color it is until we tell it that it's actually blue, green, or red. So using these images, we actually use it to make a color composite. So this is actually an image of, I think this was taken in Negros Occidental. So just to give you a background, so that's what Diwatawan's outputs look like. So moving on, so here we can see a Diwatawan data flow. There's what we call the mission operation. So this is what I'll be focusing on. So how we operate Diwatawan. And then once we get the data from Diwatawan, we process the data. So you saw that the three black and white images were turned into a colored image. So that's a form of processing the data. And then the third component is the data archiving and distribution. So this is how we get the data to its proper users. So that's the people. So in the mission operation, yeah. So we have three main activities. That's we have uploading, capturing, and downloading. So in uploading, this means uploading commands to Diwatawan. So Diwatawan is not fully autonomous. It's actually just semi-automated. Every now and then, we tell the satellite what to do. So we do that every 3 to 4 days. We upload some commands telling it what to do today, tomorrow, and then the next days. So to do that, first we need a schedule. We need to know when and where the satellite will pass over the Philippines. So this, oops. So this, so these are example passes of Diwatawan over the Philippines. So you can see the red line and the little dot moving at different places of the country. So this is, for example, these are passes taken at different days. So we need to know where they are. And then secondly, we need to know we need to know when Diwatawan will come in contact with the ground receiving station. So I think Delbert has already shown an image of the big satellite dish. So that's what we use to communicate with Diwatawan. So we wait for Diwatawan to pass over that area so we can send commands to it. It's fairly simple. Okay. So once we know the schedule, we produce these commands. So these commands are basically just codes we produce that tell the satellite how to, etc. Yeah, once it passes over once the commands are ready, and then we have a good clear pass over the ground receiving station. Once we establish a link to the satellite, we can upload these images. We can upload these commands. Okay. So once we upload these commands, the commands usually contain activities for capturing, that's one, and downloading. So for this one, this is capturing. We in advance would know what to capture. So for example, this is actually an island in Cagayan, near Batanes. So to be able to know what to capture, we need to define some criteria. So first, we want to know which target we want. So there's a target selection process, and then there's a target selection. So in target selection, of course, we need to know where the satellite will pass. So in this case, it's going to pass over these islands in Cagayan. And then we have a target database. So this is basically just a listing of, so yeah, this is an example. This is an example pass. And then the target database are just, you can imagine that these are just markers placed around the country telling us that these are what we want to capture. So when Diwatawan passes these areas, we'd want to take images of these areas. So for example, Naga, there's this Naga airport, and then maybe Surigao City. And then once we know what we want to capture, we filter them out based on the weather forecast. So Diwatawan is actually an optical satellite. So normally we don't want clouds when we're taking images because clouds obstruct the view from the ground. So we always check the weather forecast to determine which areas are actually cloud-free. Although sometimes we take images of clouds depending on what we actually want to see. Okay, so once we know this, based on these criteria, we can determine what we want to take an image of, what location. And then we now go to the capture settings. So in capture settings, we need to know the acquisition mode and the camera settings. So first, yeah, acquisition mode. So we have nadir, off nadir, and target pointing. So what are these? So these are actually types of modes of how we want to orient Diwata while it's capturing images. So first I'll discuss nadir and off nadir. So imagine you're Diwata 1 and you're flying over really, really fast over the Philippines at 7.4 kilometers per second. And the nadir and off nadir actually just means that we want to fix Diwata's position relative to the Earth. So in nadir, while it's moving, Diwata 1 will just look down, straight down, while it's moving, and it's taking pictures every few seconds. Then when it's off nadir, it's actually, while moving, it's actually tilted to the side. So you can see this little demonstration here. So while Diwata 1 is moving, you can see that the position of the rectangle or the projection of the image is just fixed. So this is what it actually looks like while it's moving and taking pictures at the same time. And then next we have target pointing. So target pointing, it's basically just pointing at a target while it's moving. So imagine you're walking and then you're locked onto, kung nakita mo yung crush mo, naglalakad ka. So tititigan mo lang siya ng ganun. So that's target pointing. Diwata 1 can do that too. And then, yeah. And then, so we choose which one, nadir, off nadir, or target pointing. So normally we just go with off nadir because it has higher accuracy than nadir and target pointing, because sometimes Diwata 1 misses its targets. Then, yeah. So we determine the camera combination. What cameras we use? Do we use the SMI or HPT? So more on that later. And then, how many images do we capture? So it's not always that we want to capture 100 images or 500 images. We know this by determining what we want to capture. So for example, Palawan. Palawan is a very long island. So it would require about 62 images to capture the stretch of Palawan. So for smaller islands, of course, it would require less. And then next, since Diwata 1 has cameras, you can actually switch its exposure time and gain like other cameras. And then capture interval, this is just a setting of how frequent do we want to capture images. So do we want to capture every second, every half second, or every 200 milliseconds or so? Okay. And then, yeah, so this is an example. The image on the left are the areas that we've already captured. So we've covered about, approximately 33% of the entire Philippines. And then here on the right is actually an example of a heat map of where Diwata 1 is most likely to pass over, and hence which areas are most likely to get captured. So the greener they are, or the bluer they are, the higher their chances of there being an image. Okay. So the next activity is downloading. So once Diwata 1 captures images, it has a memory, and it stores those images in the memory one by one. So all those 62 images are stored in memory. And then Diwata 1 produces a status report of the images. So we get this status report not right away. So we get it after it takes the images and then it reorbits, and then it orbits around the Earth and then passes over the GRS again. So how do we get the images? So again, let's go back to the schedule. We have to know when Diwata 1 will pass over the country. So during the first pass, we upload the commands. We tell Diwata 1 to capture an image during the second pass over the Philippines. And then on the third pass, Diwata 1 sends us a status report saying, nakuhanan ko na yung Romblon. So ready na yung images. And then on the fourth pass, we tell Diwata 1, gusto natin i-download yung images na yun. And on the fifth pass, Diwata 1 sends the data through the ground receiving station. So normally, we download about 70 images max. That's when we have a very good line of sight with the Diwata. Sometimes we get no images when the connection is bad. And yeah, so So yeah, so those are the three main. Yeah, that's the part of the ground receiving station mission control. So yeah, thank you for listening.
Thank you, Sir Miko.
Thank you very much, Miko. Oh my gosh, may nahulog. So ang dami na nating napag-usapan. Yung una, we talked about what satellites are, what they can do. And
Yeah.
then we talked about PhilMicrosat and Diwata 1. And then we talked about microsatellites. Tapos ngayon naman, images. Tama ba?
Yes, na kung paano nagka-capture yung Diwata 1 ng images, tapos paano nyo nababalik sa atin yung images na yun. So, so para naman, feel ko very curious na kayo, very interested na kayo about satellites. So, we can entertain one question from the audience. Yes, sir. Immediate talaga.
May microphone po tayo, sir. And if you can address it to the speaker, it would be much better.
Good afternoon sa inyong lahat. I'm Kahiro sa PDP. I'm a social entrepreneur. Thank you for the education, telling about the WATA and the CubeSat and the microsatellite. My inquiry is, kasi nakakapanood din ako ng sine, yung ginagamit sa mga spy network. Nakaka-capture pati yung image, pati yung sinasabi doon sa ground. O pwede ho ba yun i-develop yung mga ganun sa Pilipinas o meron na tayo na ginagamit ng AFP o PNP?
Miko, do you want to answer that question?
Or
Anyone from PhilMicrosat?
Or are you guys in the liberty to
Is
answer
this
that
above your pay grade?
Well, I'm not sure if I have clearance to answer that. Well, first off,
Meron na ho ba tayo o wala pa?
well, I don't think we have one. Well, first off, Diwata 1 is mainly used for environmental
Yeah,
applications.
I understand as what nandun sa presentation. Ang tinatanong kung meron na o wala pa na capability ng Pilipinas tungkol sa ganung bagay.
Well, I believe we still don't have that
We don't have.
technology. Yes.
So that is something to develop pa.
Yes.
Thank you very much.
Okay, so we will reserve other questions no for later, since we have a dedicated portion for that. We have two more speakers.
Yes, we have two more speakers. Very short speeches from our two remaining speakers.
So save your questions. So medyo intellectual stimulation lang yung ginawa natin.
So yun, like we've said, we've talked about satellites, the different kinds of satellites that the Philippines has, the image capturing process, and now we move on to how the program processes the images taken by our satellite. So the next speaker is one of Diwata 1's engineers, Ms. K. Christine Verhel. Ms. Verhel is PhilMicrosat's mission and payload development engineer. She is part of the team who designed, developed, and drafted the missions of microsatellites Diwata 1 and Diwata 2. She completed her master's in cosmosciences in March 2017 at Hokkaido University in Japan. And she took her undergraduate degree in applied physics in UP Diliman. So everybody please welcome Ms. K. Christine Verhel.
Hi, good afternoon, everyone. I'm Kay, and in my presentation, I'll talk about Diwata 1's images, the cameras, and how we do research on the images of Diwata 1. So before talking about that, I want to know how many of you have cell phones? Can you raise your hands? Siguro naman lahat tayo may cellphone. And I also think na yung mga cellphone natin may camera, no? So I have here, my phone is an iPhone 7. And yes, nakalubag-lubag. So, ito yung back ng iPhone 7 ko. So, you can see there's a camera here. And using that camera, I took a picture this is a picture that I took last week. So, well, so sunny. And I want you to look at this area here. So when I zoom in that area, 8 times zoom in, what we see is this, I think this is an island. I don't know, I think it's an island south of Japan. But what I want you to observe is that when I zoomed in that picture, you can notice that there are squares in the image, right? Well, pag nakita mo siya, ang una mo sasabihin, ay, pixelated siya. So we can actually see the pixels or the picture elements. So each pixel has a value. We call it digital number. And for this image here, it has 3 values, one for red, green, and blue. So now, okay, wait. Okay, so now, when we take an image, normally, of course, there would be light hitting on a particular target that we want to take an image of. So light, or the visible light, is part of the electromagnetic spectrum. So the light that we see, as I think earlier presented by Miko, ranges from 400 nanometer to 700 nanometer. So the electromagnetic spectrum ranges from gamma ray, X-ray, ultraviolet, then the visible light that we see, infrared, microwaves, and radio waves. So you can see there the different wavelengths for each particular color. So violet, blue, green, yellow, orange, and red. So actually, itong visible light is what we see when, since umuulan ngayon, so pagkatapos ng ulan, we observe a rainbow. So essentially, the light is reflected and refracted by the droplets of the rain. That's why we observe the rainbow. Okay, now, going back to the image that I showed earlier. So this image here is a colored image. And this colored image can be broken down into 3 channels or 3 bands. That's for red, green, and blue. So as you can see here, for the blue image, mas maliwanag siya. Kasi mas blue yung image dito. Okay, now, Diwata 1 has 4 cameras. So medyo hindi lang halata kasi medyo madilim, no? So baka pwede bang i-turn off yung light dito? Or kung hindi, okay lang. So Diwata 1 has 4 cameras. Yeah. So one is the high precision telescope. We call it HPT. So one here. And then the space-borne multispectral imager, SMI, with liquid crystal tunable filter, LCTF. SMI with LCTF. It has a wide field camera, so it's like a GoPro. The wide field camera, not Diwata 1. And a middle field camera, so in short, MFC. Okay, so just to give you a perspective on the size of the image taken by Diwata 1. So for SMI with LCTF, the swath or the field of view of the image is 32 by 43 kilometers, and it has a ground sampling distance of 66 meters. So GSD, or ground sampling distance, it means that it's the size of a pixel when projected onto the ground, okay? So it's 66 meters. So comparing this image of SMI to HPT, this is the comparison. So you can see HPT's image is very small. The field of view is 1.9 by 1.4 kilometers, and the GSD is 3 meters. Okay, now, okay, just zooming in on that HPT image. Now comparing this image, okay, so this image is taken by MFC. Field of view is 1 to 1.9 by 91.4 kilometers, and GSD is 185 meters. And then comparing this image of MFC to that taken of SMI, so mas malaki yung image taken by MFC. So this is the image taken by SMI. Okay, and then lastly, this is a sample image taken by the wide field camera. So you can just observe that we can see the whole Earth in the image. Okay, so now I will further discuss 2 cameras, because Diwata 1, even though it has 4 cameras, the science payload, there's the science cameras, are 2, that is HPT and SMI. So SMI, again, sinabi ko na yung field of view, but what you can see here is it has 2 lenses for 2 CCDs and 2 filters. So since it has 2 filters, one is in the visible region, as I discussed earlier, from 430 to 740 nanometers, and then the other one is in the near-infrared region, from 730 to 1020 nanometers. So what's the meaning of that? So it means that we can actually set a particular wavelength. For example, we want to take images at 500 and 600 nanometers. 500 in the visible, using the visible CCD or visible CCD of SMI, and then 700 for near-infrared. Then we can, when we set that, what the camera does is that it will just let, say, 500 nanometer pass through and filter out the rest. Okay? Okay. So, and then for, okay. So we also have the high precision telescope. So as you can see here, or I'm not sure if you can observe, but it has 4 CCDs for near-infrared, for red, for green, and for blue. Okay. Okay, so the first thing, or what I'm showing now is a sample image taken by Diwata's HPT. So this is the red, green, blue, and near-infrared. So this is an image taken in Bulacan last year. So it's one of the 30 images that was taken using target pointing, as discussed by Mika earlier. So the first thing that can be done to Diwata's images is to create a color composite, so colored image. So as I showed earlier, the colored image that taken by my iPhone 7 can be broken down into 3 bands, right? Now we have 3 bands, red, green, and blue. We want to create a colored image. Red, green, and blue, and then we have a colored image here. These are some of the images taken, some sample images taken by Diwata 1 in Iloilo, in Cavite, and in Palawan. Okay, so one of the things that we do with these images that Diwata 1 is taking is we try to observe post-disaster damages. So in this example, what I'm showing is an image taken by HPT last October 24, 2016, after Typhoon Lawin hit the northern part of Luzon in Cagayan. So this is the image taken. It's around 866 meters from Cagayan River. So from this image, you can see that these are actually a crop field, and these are floods. Okay. So again, this is the HPT image, and we also try to do image classification. So from the image that we have here, we try to classify if it is vegetation, bare land, water. So as you can see here, yeah, this is, we were able to classify it as water. Okay, so that's for HPT. Now for SMI, again, similar to HPT, the first thing that we can do is to create color images from the images of SMI. So I think this is the image shown by Miko earlier. Okay. So sample images taken by SMI. This is a sample, this is an image of Mount Pinatubo. So it's actually a stitched image. So apat yung images na nandito, in-stitch lang. And also in Bicol, although hindi ko lang mabilang ngayon. And also in Manila, so Feb of this year. Okay. So now, as I said earlier, for SMI, we can actually capture images at different wavelengths. So what's the importance of this? So imagine when light hits a plant, for example, a plant. When light hits a plant, the light, as I said earlier, is part of the electromagnetic spectrum, right? So the visible part is mainly absorbed by the plant. So actually here, the visible part, blue, green, and red, is mainly absorbed. However, there's a bump in green. That's why we see the plant as green. But mainly in near-infrared, all of the light is reflected back. Okay, and so that is a characteristic of a healthy vegetation. Now, if you're looking at an unhealthy vegetation, that reflected part of the light in the near-infrared region is less. So by utilizing those characteristics, we can actually monitor the health of a plant, or even classify if what plant is which. I mean, if like a certain plant has a certain reflectance different to another, we can do classification. So what I'm showing here, so utilizing that information, there are different what we call vegetation index. So one example is this NDVI. It's short for normalized difference vegetation index. So it's actually near infrared minus red over near infrared plus red. So what this index tells us is that if its value is high, the vegetation is healthy, and if it is low, it's unhealthy. So, so using that information, now that we have a camera that is able to capture the scenery at different wavelengths, we can actually observe or obtain the spectral reflectance of a particular target. Okay, so sample again of images taken by SMI at different wavelengths. Okay. Okay, and then this is the calculated NDVI using 660 nanometers and 860 nanometers. So actually, these images are images in the western coast of Negros Occidental. So it is, we were able to take 30 images with 6 wavelengths using off-nadir pointing. Okay, so Diwata 1, this is a sample image of Diwata 1 where we calculated for the NDVI when it passed by Occidental Mindoro. And we're zooming in at this area here. So in this zoom-in area, so this is Semirara Island. So the blue part of this image here is actually ocean. So what you see here, the black line that you see is the boundary of the island. And you can observe that there are gray areas that are, or already exceeds the boundary. So actually, there are, when we looked at the image of the island, there are, we observe, or this thing that we see here, we observe, what do you call this? Reclamation activities in the island, because there's an ongoing mining activity that's being done in Semirara Island. Okay, so some sample, this is a sample image taken by SMI in Ilocos Norte, and the corresponding NDVI and GNDVI. GNDVI, NDVI near infrared minus red. GNDVI near infrared minus green. And then the land cover classification of the same image. Okay. Also a sample image taken by SMI along Central Luzon, and the corresponding NDVI map as well. In Palawan. And as Miko shown earlier, currently now we've already taken multispectral images of the Philippines, or 34.4% of the Philippines land area. Okay, so the main goal, actually, our main goal in the project, I think, is to relate actual field measurements on the ground to satellite images. So by actual field measurement, if we want to measure the water quality, or if we want to measure, or if we want to know the health of the vegetation, we don't have to actually go there. So normally, if you want to, for example, know the water quality in Laguna Lake, you go there, you have your instruments with you, and then you measure, say, turbidity. Of course, we don't want to do that all the time, or we don't have maybe the money to do that all the time. So what we want to do is to relate the images that we get from satellite data to those data that we get when we do field measurements. So I'll be showing just one example, a case study in Laguna Lake, wherein this image here is the estimated turbidity using the red and green band ratio, so red divided by green, of Laguna Lake. But this image here is taken by Landsat 8. So using that image of Landsat 8, we were able to get a relationship of turbidity to the satellite image. So now, using that relationship, we were able to get also a turbidity or an estimate of turbidity in Laguna Lake using the Diwata 1's images taken April 11, 2017. So that's last year. Okay, and so this is, we tasked Diwata 1 to take images on April 11. This is images taken by Landsat before and after Diwata 1 passed by the particular area. So what we're showing here is, of course, it's not, when we do observation, it's not necessary that we just look at Diwata 1. So normally, we also look at different data sets and relate what we get from Diwata to other satellites as well. Okay, so right now, that's Diwata 1. What we're doing now, we're also developing Diwata 2. So actually, this is just some images of the test being done by now. I just arrived last night from Japan, and we've already done vibration tests. So as Delberg showed earlier, the satellite undergoes different tests in order for us to make sure that it will work once it goes up to space. Okay. So actually, yeah, that's it. That's my presentation. I hope you did not get bored. And yeah.
Thank you,
Ms. Kay.
It's so wonderful to hear from the brilliant young minds in space technology
Meron talaga silang
in the
basbas ng
Philippines.
Diwata, no?
So from the brilliant young minds of space technology, we will hear from another brilliant young mind. So the next speaker is the program leader of the Phil Microsat program, and he is the acting director of the Department of Science and Technology, Advanced Science and Technology Institute, or DOST-ASTI.
So please help us welcome with a round of applause, Dr. Joel Joseph Marciano Jr.
Ikaw makiklik. Pakiclick na lang. May clicker. From a brilliant young mind to a dilapidated old mind. So, okay, is it running? May JSM. Ba't wala na? Nasa drive. There you go, yan. Okay. Pakiclick. Now, medyo kakaiba yung talk ko. Let me give you, perhaps this is something that maybe is in your mind as young people. Bakit ba tayo nasa space? No? People are enamored by space. This is a perspective-setting talk. I'm approaching it from the point of view of value creation from the development of small satellites for Earth observation. So ano bang value ang nakukuha natin and nakikreate natin by building small satellites? Okay, let me start by describing something everybody here is familiar with, computers. Lahat tayo gumagamit ng computers. This is a computer room, di ba? go back to your school, siguro hindi na CRT monitors, LCD na, mga ganyan. But you have rooms full of computers that you use, or classroom, etc. Okay, yan ang alam natin sa mga computers. But then we also hear about mga server farms, no? Mga installations, mga data centers, rows and rows of high-performance computers, servers, okay, for data repository. Yan yung tinatawag na cloud. Diba? Pag sinasabing cloud computing, you're not computing on a desktop, your computation goes somewhere over the internet to some remote data center, dun kino-compute. Tapos bumabalik sa'yo information na. That's the cloud. Okay, so the face of computing is changing. In fact, computers fit in the palm of our hands now. So everybody here should start thinking differently of computers. Hindi lang yan yung mga laptops or desktops na ginagamit natin. We're sitting right here, I'm standing right here, I have 2 computers in my pocket. Okay, 2 computers in my pocket. What are those? My cell phones. I don't know where you were around 2001, naglabas ang advertisement si Nokia. They were advertising the Nokia 9500 communicator. And at the end of that commercial, sabi nila, this is what computers have become. That was their tagline. It was referring to a cell phone that had a keypad in it na QWERTY. No? And that resonated with me. I also like telling this story because I'm a big tennis fan. You know, watching Wimbledon on TV, the tennis tournament, 2006, Roger Federer won the championship. And as he was parading the trophy around the grounds, the camera panned at the audience. And the audience, I was surprised, I was not looking at Federer, I was looking at the audience. We're not holding cameras. They were holding cell phones. And they were taking pictures of Federer holding up the trophy with their cell phones. And right then and there, sabi ko sa sarili ko, oh my gosh, Canon, Nikon, Yuga, Olympus, you guys are in trouble. Point-and-shoot cameras, except yung mga enthusiasts sa mga SLRs, you know, yung mga point-and-shoot cameras yan, malapit na mawala yan kasi our cell phones are turning into cameras. Right? That was then. And look how it is now. We probably hardly even call anybody on the cell phone anymore. Right? Lahat dinadaan through instant messaging, right? I don't know, when was the last time you actually called somebody on the phone? We used to place calls on the phone. But computers, right, are becoming so pervasive. They fit in the environment. They become embedded in the environment. They fit in the palm of our hands. Now, one more thing. Anong ibig sabihin pag nagko-compute ka? Dati inisip natin kailangan some fancy computation. Meron akong algorithm na sinosolve. Meron fancy simulation. You're doing some CAD modeling, some high performance graphics rendering. No, you don't have to be doing that to be computing. Computing has become more participative. You can be logging onto Facebook, updating your status. You can be sending out a tweet. You're computing. Ang tawag nila dyan, social computing. I don't know if you can read that. Social computing. Why? Because the moment you send a tweet, you're triggering a chain of computations in the cloud somewhere, right? To parse the characters that you press on your phone and turn it into a certain format. That's computing. Okay? So what they say with computing is that it's becoming a vanishing technology. It's going the way of the light bulb. What does that mean? Electricity. Noong unang panahon, napaka-exclusive ng electricity. Mga mayayaman lang meron. Pero ngayon, nagpunta kasi isang lugar, walang kuryente, magre-reklamo ka. Napaka-backward naman ng lugar na to, wala pang kuryente. Right? Or what examples of other technologies you can think of that way? Cell phones. Right? Pag pumunta kasi isang area na walang signal, sabi mo, ba't ganon? Na medyo, ano pa rin, old school pa rin dito. Another thing, internet. We're taking those things for granted now. People are being born into this world thinking that those things are everywhere and constant. Right? Hindi na nakita kung paano sila pinanganak in technologies. Yan yung curve na yan. Right? From being exclusive to everyone has it to a vanishing technology. You go to a coffee shop, there's no Wi-Fi. Sabi, walang kwentang coffee shop to. Right? Or, punta ka sa coffee shop, may bayad ang Wi-Fi. Wag tayo dito, next time doon tayo sa libre. Kasi kailangan ko yung internet eh, di ba? You take it for granted. You assume it's everywhere. Okay? We have moved from this mainframe era, ito yon. You see how over time, medyo decay na siya. Ang paradigm nun is isang computer serving many people. Kasi napaka-expensive ng mga computers dati. To a personal computing era, wherein you have one person, one computer, that's really what the PC means, personal computer. Naging affordable siya so that every home had a computer, is able to have a computer. That was in the 1980s, latter part of the 70s, into a ubiquitous computing era where one person has access to many computers. I'll just exaggerate this point. We had a professor from UC Berkeley who 10 years ago famously said to us, in 20 years, in a course of a 24-hour period, each and every one of us would have interacted with at least 10,000 computers. In a 24-hour period, as you go over your daily lives, you would interact with 10,000 computers. How is that even possible? Magla-log on ka to 10,000 computers and gano'n. No, kasi kailangan natin baguhin yung tingin natin sa computers. Hindi yan yung mga laptop, desktop, no. You walk into a room like this, the lighting adjusts because it senses the presence of people and the number of people. The air conditioning adjusts automatically because there's sensors embedded in the background, triggering a chain of computations, counting the number of people based on the carbon dioxide level in the room, and adjusting temperature and lighting. Right? Several years ago, when I was in Berkeley, they had this experiment. They were bringing cans of paint into the lab. So, bakit may cans of paint in a wireless communications lab? Because they built sensors, very tiny sensors with no batteries, and they started sprinkling them into the paint, mixing it into the paint. And they are painting a wall. And the wall had sensors. What did that wall do? The sensors were harvesting energy from ambient vibrations. And they were sensing the presence of people passing by the wall. Okay? That's how you interact with 10,000 computers, okay, in a single day. Okay? In the future, clothes will be computational devices sensing our biophysical condition, right? Wallets are computers. That's how we interact. Okay. I like repeating this quote. The most profound technologies are those that disappear. They embed themselves or they weave themselves into the fabric of everyday life until they are indistinguishable from it. Okay? By Mark Weiser, so-called father of ubiquitous computing, Xerox Palo Alto. Okay. Think about that. So now my question to you, where else are computers vanishing into? Well, you're in a space forum, so you should be thinking into space. This is Diwata 1 vanishing into space. Okay? People call it the Philippines' first microsatellite. First of all, I used to like that. I don't like it anymore. First of all, I don't like the term first because I'm more interested in the second, the third, the fourth, the fifth. Because mamaya baka first and only lang yan, di ba? So that's not good. But I also like to think of it not as a satellite, but as our first computer in space. Okay? That's my perspective of it. Okay? As an engineer, it's a computer. This is the block diagram, 1, 2, 3, 4, 5, 6, 7, at least 7 computers inside that box. The computers do a range of functions from controlling the payload to controlling the communication system, adjusting its orientation, many things, controlling the power supply. So it's a whole bunch of computers in space. Okay? So you think of space, you think of countries like US, Russia, Japan, India, the European Union, even China. You ask the Philippines, you know, with going into small satellites and space technology, we ask the question, what could we be in it for? Why do that? Right? What do you think? I come from computers to, well, data. It's a rather strange answer going into space. Because the moment you have computers, generate data, right? Okay? What kind of data? Satellite images. previous speakers talked all about these images. I'm not going to repeat them. So these satellite images, taking pictures at different wavelengths, right? Measuring the environment from volcanoes erupting, vegetation in the seas, turbidity of water, right? Spying on other countries. Don't quote me on that. Okay, ito, flooding. Nakita nyo na siguro yan kanina. Ito, nakita nyo rin kanina, yung Semirara Island, di ba? Kung saan sila nagtatapon nung hinuhukay nila. Di ba? Kasi pag nagmamine ka, nagbimina ka, yung lupa na tinatanggal mo, saan mo nilalagay? In this case, sa dagat. Yun, sa may parang reclamation area. Tama ba yun, Kay? O, tama yun. Nandito yung coal mining. Oh. Okay? So that's data. That's better understanding of our physical world. Okay? Right. So far, 34% na yata, hindi na 28%. No? Ang na-image all over the Philippines. Various applications from assessing damages from typhoons, land cover classification, water quality assessment. All of these right now are really research objectives. You have to understand that building satellites is not an overnight activity. When we go into space, we have to have the endurance and the stamina for it. Walang 3-in-1 sa space. Walang instant noodles sa space. Okay? Hindi yung gagawa ka ng isang satellite, superpower ka na kagad. No. You look at India, decades. Vietnam, starting, several years already. Right? Indonesia, again, almost more than a decade. Right? So that's how it is. Statistics ng mga images na process si Diwata 1 and distribute. Okay? I think napakita na rin sa inyo kung nasan yung website. Pwede ka mag-request ng image. We'll try our best. The orbit of Diwata 1 is always a challenge kasi ISS orbit, and probably na-explain na sa inyo kanina na ang revisit is not that regular. But with Diwata 2, hopefully we can do better. Okay? Different institutions that have logged onto the site and downloaded images. Universities, NGOs, government agencies. Okay, saan ginagamit yung mga satellite images? Ngayon, kaninang umaga, meron yatang talk on AI and machine learning, right? There's increasingly heightened activity on applying deep learning, machine learning on satellite images. Every pixel is a data point, right? You see here investments on space technology between 2014 and 2015 increased by 23 times. This is in millions of dollars, so that's 2.3 billion, 2.3 thousands of dollars, so 2.314, that's 2 billion, right? Because of companies like SpaceX, OneWeb, O3B. You have so-called new space companies as opposed to old space companies. These are startups. What are they doing with satellite images? For example, may isang company na ginagamit niya yung pictures ng mga parking lots, mga kotse sa parking lots, by counting them in very good temporal intervals, kaya niyang, through some fancy algorithm, i-predict niya yung profitability ng isang retail establishment by the number of cars parked outside. Okay? So pwede ka naman pumunta dun sa SM, magbilang ka ng kotse, di ba? Right? Pero ito, satellite images ang ginagamit. Very comprehensive view. Right? E mababalikan mo yung previous years kung nakuhaan yung area na yon. So with that, you can train your machine. The moment magbilang ng ganitong kotse, at saka baka pwede pa kung anong klaseng kotse yung nakapark. Di ba? It's an indicator of economic status. Right? Kung puro SUVs or mga high-end brands yung mga kotse, medyo ano dyan, no? Ano pa? Yung mga oil tanks na ganito, lumulubog daw yung takip niyan kapag depending on the volume of oil inside. So tinitingnan nila yung shadows. The shadows. By looking at the shadows, you have an estimate of oil inventory. So pag nagtataas ang presyo ng langis, makikita mo, makukorelate mo, well, gaano ba kalaking inventory natin ngayon? Justified ba yung pagtaas ng presyo ng langis? May stock ka pa eh. Bakit ka nagtataas ng presyo kung may stock ka pa? Hindi ka naman bumibili ngayon. Di ba? Things like that. Okay? Estimation of economic activity, poverty prediction, yield prediction through NDVI, vegetation indices, etc. You can form your own company in the future leveraging on this kind of data to create some new application that other people have not even thought about. mga proxies, yung mga ilaw sa gabi, naka-capture ng satellite from different communities and areas. It's a proxy for household income. So, imbis nang mag-census ka, magpadala ka ng tao sa mga different communities, magtatanong, kakatok sa pinto, anong household income nyo? Right? Census yon. May sampling, etc. Sabi nila, kaya mong ma-infer yung same information by just looking at satellite images. Tingnan mo yung level ng ilaw sa gabi. Okay? That's data science. It's data analytics. Okay? Data. Sorry. Na-distort. Sabi nila, data is the new oil. Yan ang bagong, in an information and knowledge society, data is the new oil. Whoever holds data has power because data is converted to information. Information is converted to better policies, better programs. Okay? But it's not just about the data. I say data, pero hindi lang data. But remember that, data. It's also about developing local industry. Okay? Ito ang nakita niyo siguro sa talk kanina, mga locally developed electronic components that will fly with Diwata 2. Okay? Hindi mo pwedeng gawin lang sa lab to. Kailangan kausapin mo yung manufacturer, yung industry partner. So ngayon, yung mga local companies, na electronics companies, nasa-challenge tuloy sila. Kailangan gawin nila reliable for space. Okay? That's how we work together with industry. Kung walang ganitong programa, industry will be doing whatever it is they're doing for the past 20 years and walang bagong challenges masyado. So space poses entirely a new set of challenges. Okay? Sun aspect sensor, attitude control unit. Okay, we want to build this PHL-50 bus so that we can reuse it for future space missions of the Philippines. The bus, probably as explained to everybody earlier, is the electromechanical structure of the satellite. Okay? Building a space heritage by identifying key components of the satellite that we can build locally using available materials, capabilities, and resources here sa Pilipinas. Hindi 100% kaya lahat. It doesn't make sense. Even Indonesia, when they launch their satellites, off-the-shelf components galing sa Japan, Germany, etc., but they contribute something locally developed. Hindi lang lab nila, pero yung industry nila. Okay? Right. So let me speed up. Third thing, so data, industry, third thing, tao. Okay, people. Pag gumagawa ka ng satellite, nade-develop ang mga tao. Right? Ayan, kita mo, ang daming fields involved, di ba? Hindi lang yan isa. Okay? But we're looking for certain kind of people. Ang tawag namin sa mga tao ng T-shaped people. Hindi ka pwedeng I-shaped. Ibig sabihin ng I-shaped, vertical ka lang. Vertical. Ibig sabihin, magaling ka sa ginagawa mo, magaling ka sa alam mo, pero alam mo ba yung iba? Kaya mo ba mag-work with others to solve bigger problems, bigger challenges? Kasi kung ikaw lang, no, electrical engineer ka, mag-isa ka, o mag-isa kang mechanical engineer, hindi mo kayang gumawa ng satellite by yourself. Okay? You need to work with people from various disciplines. So we look at electrical, electronics, mechanical, materials engineers, we turn them into systems engineers. Okay? Remote sensing scientists, they learn new tools, data science and data analytics, AI, machine learning. Right? So they become data scientists. That's how we build satellites. You need T-shaped people. And for a country tulad natin, admittedly, we're catching up. Right? Hindi tayo pwedeng kanya-kanya, sari-sarili. You have to have empathy for what other people are doing and we need to band together to solve bigger problems. Okay? Ito yung mga T-shaped people, just so it's clear what that means. They have a principal skill that describes the vertical leg of the T, depth of expertise. They might be mechanical engineers or industrial designers, but they're also so empathetic. They care about what other people are doing and what their needs are, that they can branch out into other skills. Right? Example nandito, anthropology, etc. Okay? They are able to explore insights from many different perspectives and recognize patterns of behavior that point to a universal human need. So ang ibig sabihin lang no, you branch out from your expertise, you work with people from other disciplines, you have the skills to do that, and you can solve bigger problems. Yung science and technology is increasingly becoming collaborative. This is a chart showing the published papers in clean energy. Chemistry, 18.6%, material science, 24.2%, physics, 14.5%, energy, 10.4%, engineering, 7.9%, chemical engineering, 7.5%, agricultural, biological sciences, 1.7%, immunology and microbiology to clean energy. Does any single discipline have a monopoly over clean, renewable energy? Hindi. It's conglomeration of all these fields as you look at the published literature. So, if you become a T-shaped person, as a T-shaped institution, you're not just, in this case, you're solving a bigger problem. You're solving a clean energy problem as opposed to solving a physics problem. Okay? As opposed to solving a chemistry problem. Right? And that's how we create societal impact, by solving problems like clean energy. Right? But you need all of those skills working together. So interdisciplinary S&T, just like building satellites, is required to address complex problems and for larger societal impact. The research process is therefore becoming more and more complex. We need T-shaped researchers and innovators to use new knowledge in various ways, increasingly across disciplines and institutions and borders. Okay? That's one takeaway for everybody here. Okay? Become good at what you do, but work with others to build bigger things and solve bigger problems. Right? Nakita niyo yung microsat, inherently interdisciplinary. From environmental scientists, geodetic engineers, electrical electronics engineers, mechanical engineers. We collaborate also with Japan, Hokkaido University, Tohoku University, Kyushu Institute of Technology, academe, research institutions, etc. That's how we develop people who become T-shaped. Okay. Lastly, okay, again, data, industry, people. Last thing, enabling environment. We want to build an enabling environment for interdisciplinary research and development. So space technology makes us rethink the way we build our spaces. Pun intended, no? Space technology makes us rethink. If hindi na magets and wait in line for your turn to be launched. Pero ganun na yung impact of these companies launching rockets. Hindi lang siya exclusive domain ni NASA, ni JAXA. There are startups that are launching satellites. Okay. Finally, this is some kind of recipe for innovation, value creation ng microsat team. No? A design thinking mindset for lean satellites. That means rapid experimentation, iteration, improving, continuously improving, plus T-shaped people, institutions, plus enabling environment. Okay? Underpinning all of that is government support. And we're happy that our government is actually supporting this kind of activity. It goes beyond space. It's not just about space. If you take anything away from my talk, it's about enabling ourselves with data, information, improving our capacity for innovation by teaching people to work together, bring their best to the table, solve bigger problems, right? And helping our industry. The industry might not end up building satellites, but who cares? They might end up building better electronic systems because they learned about space technology from us. Right? They might build better cell phones. They might build better washing machines. They might build better flat irons that compete in the global market because they learned from the discipline and the rigor of space technology. Those are long-term impacts. No? Again, we cannot be using a short-term lens to view space. Okay, hindi pwedeng instant noodle, 3-in-1 coffee, kailangan ko na ngayon. Right? We have to be in it for the long term. Okay? And habang nandito yung mga nagsalita sa inyo kanina, these guys are, di ba, are bet for the future. Not somebody like me, but the guys who spoke to you earlier today, the whole day. They're the ones, no? Staking the rest of their careers on something like this. Right? Right? And they're inviting you to participate. It's a long haul. Okay? So with that, I think that's it. Thank you very much for the opportunity.
Thank you, Dr. Marciano, for that very insightful presentation on the Phil Microsat project.
Very rousing.
Oo nga eh. Oo, rousing, it's brilliant, it's
Fresh.
it's fresh.
Nakakapagbagbag damdamin.
Try again.
Never mind.
So I hope that encourages everyone in the room, no matter how young, no matter how not too young, to engage in our space program. And now to call on our last speaker for this session to speak about amateur radio and amateur radio in space. May we call on Engineer Leo Almazan. He is one of the Department of Science and Technology's Balik scientist. So
Let's give him a round of applause.
Engineer Leo Almazan.
Thank you. Thank you. Thanks to Joel. I'm one of his enabler. Joel has been very nice to us enablers from the get-go. So what I'm going to talk to you about is one segment of what he was talking about. As you can see from his... Anyway, from one of his slides, he shows components from the Diwata satellite, the Diwata 2. There's an amateur radio component and two other components. Well, I'm going to be talking about that amateur radio component. So if you guys are ready. Are you kidding? Anyways, jeez. Meron ako dito. I'm glad I... Kala ko. Hold this, please. Okay, thanks for putting up with the glitch here. Anyway, here's my presentation, Amateur Radio in Space. That gold letters back there, WA6LOS and DU3 Zulu X-ray is my amateur radio call sign. The WA6 is from the US, DU3 is from the Philippines. So, okay, what is amateur radio? Ano bang amateurista? At I know madami dito, they're very curious. Amateur radio, ang tawag sa amin ay ham radio operators also. And it describes our use of the amateur radio spectrum for the purpose of non-commercial. Hindi kami binabayaran. So we can exchange messages. We could do wireless experimentation, be it a hobby. Also, we self-train. Although some of us are professionals, there are students that have not even graduated from high school that are into this project or hobby, and also for our own private recreation. As you can see from the slides, from the, this is it right here. Oh, anyways, as you could see from, oops. From this slide, from left to right, that's a girl or a lady who has a very nice amateur radio station. Very, very expensive, very sophisticated. And on the center slide are two stations. One is a very low power station, and he uses Morse code. That's one of the part of our hobby. And the one to the bottom center is a what we call home brew, or self-built from scratch radio. Right? So you don't have to be expensive. Another part of the hobby that I like, and I have been doing this for quite a while now. In fact, last May we were able to talk to the International Space Station, high school students from UPIS and Holy Angel University, and some of the engineers and scientists here, especially that guy right there, was able to talk to the ISS astronauts. Okay? In fact, he was greeted happy birthday by the astronaut during his conversation with him. Okay? Again, you could build your radio from a kit like the one to the left. Very easy to use. Basta marunong ka lang mag-soldering. Madaling gawin yun. And also from scratch, kung talaga marunong ka na, you could build this thing from a printed circuit board. Sino dito ang into the hobby of electronics? Meron ba? Electronics ng hobby? Computer siguro, but not electronics. Anyways, from scratch you could do this thing. And also, experimentation is what amateur radio is all about. Maski palpak yung ginawa mo, basta may natutuwang ka, that is good enough. Failure is one of the options. Okay? Parating intindihan nyo, when you do your own research and development, failure is one of the options. Okay? You don't have to be successful all the time. Okay, yeah, my experience with amateur radio is since I was 12 years old. Okay, I was in the U.S. when I got my first license, WN6YJC. I was 12 years old. I was in junior high, and those are the countries that are associated with all the 6 continents on Earth. All right, there's 6 continents in amateur radio. Top left is North America, and that's from, I believe, Texas. Next to it is Yankee Victor 4, which is from Venezuela. And the one next to us is India Kilo 2, which is in Italy. And the bottom one to the left is Victor Kilo 4, which is from Australia. And next to it is Japan Alpha 1, which is from Japan. And then 3 Charlie 0 is from Africa. So this you could do. Okay, sometimes I'm in my radio till 2 o'clock in the morning trying to talk to the Europeans. Ayaw nila akong bitawan. So they like to talk to the Philippines. So sometimes I'm there till 2 o'clock in the morning. And this is one facet of amateur radio that a lot of people here in the Philippines like. They like to build antennas. Okay? You could build a dipole antenna, which is on the top part of this slide. It's very simple. You need 2 wires. Connect it to a coaxial cable, make sure it's the right measurement, and you have an antenna. Or you could go quad antenna right there, lots of wires, right? But it's very, very powerful antenna. Or right here in the Philippines, the one in the center, ang dami kang makikita ganito sa Pilipinas. Because everybody is into VHF. Either handheld radio sila or naka-mobile radio sila. Nag-uusap sila from morning to night. Madaming chismisan pa. And madaming nagliligawan pa. Anyways, my antenna is the one to the right. I have that at home. I built it from 3 different kits. So I put it up, and by the way, that tower there has a tram system, elevator system yan. Nabababa ko yan by cranking it up or down. Kaya yan, nakababa. Kasi pag umuulan, babagyo, I have to protect my antenna. I have to bring it down. Kasi mahal yung mga pyesa. So I have to do that. Okay. And amateur radio is everywhere, right? The one to the upper left, yan, nasa aeroplano yan. This guy is using his radio to talk to whoever he can talk to. I used to fly for the U.S. Navy. I flew S-3Bs and C-9 Bravos for the U.S. Navy. And when I'm not fully participating in the flight, I just use the radio and call people that I know. Aeronautical Mobile. This is Whiskey Alpha 6, Lima Oscar Sierra, Aeronautical Mobile. Who is listening? Yun ang ginagawa ko. I talk to, sometimes I get call from the U.S., sometimes I get call from Japan. And the one to the upper right is inside the space station. We have an amateur radio in space, in the space station. Or you can have one at home, just like this. And this is a top-notch amateur radio station. Gagastos ka lang if you want to do that. And like me, I have HF, VHF, UHF radios in my car. So I can talk. So when I go home tomorrow, as soon as I hit the road, I'll be talking. And once in a while, as I get lucky, I talk to Europe. Pag nasa viaduct ako, I can talk to anywhere. Basta nasa viaduct ako. Anywhere from Australia, Japan, the Middle East, and Europe on my radio in the car. And so, you know, amateur radio and public service is synonymous. Pag amateurista ka, you have this obligation to help out because you're a communicator, okay? We are very, very well known. Even dito sa Pilipinas, during Yolanda, Yolanda, at saka nung sa earthquake sa Bohol, the amateur radio were the first station to talk to Manila. Kasi bagsakan yung mga cell tower. Okay? The critical is the first 48 hours. Kahit saan ka pumunta. Whether it's the earthquake in China, the recent hurricane disaster in Puerto Rico, and Haiyan or Yolanda, first 48 hours critical. Kasi I was part of the network during the Haiyan. I was here in the Philippines when it happened. So I volunteered my expertise to a local amateur radio club, and we were passing data from a ham from Tacloban to Manila, because families were worrying, kamusta ba yung mga kamag-anak ko o yung anak ko? They have no knowledge of what happened to them. Okay, there were 6,400 people that either died, injured during Yolanda. Okay. Some of them were found 2 months or 3 months after the fact. So, kailangan mo ng communication. So, it says in there, when all else fails, amateur radio works. Okay? So, the one on the bottom left is what we call an APRS. That's automated packet reporting system. It uses GPS. Kung meron kang gadget na ganyan, you could tell wherever he is. Okay? Ang kagandahan niyan, hindi lang nagre-receive. He could also transmit information to you. Data information in the digital world. Okay? Pati yung weather, nare-report niya sa'yo. And then you could also report to him kung ano yung weather. Right? That's the good part about APRS. And then the one to the bottom right is what we call a go box. We have several of that at Holy Angel University because we are one of the emergency node. And hopefully we will have that also in Cebu and Mindanao. So that is the thing at amateur radio can do. We have very, very small equipment now. Like Joel was saying, everything is getting smaller and smaller. And then here is a amateur radio in space. The first one, bata pa kayo, so you don't know what Sputnik is. All right, that's the first. In fact, the Russians that I was talking to, or during the forum when I was speaking, they really, very, very proud when I mentioned Sputnik. This was in the 60s, early 60s. As you could see, those are ham radio operators in Leningrad, and they were able to receive only. Walang transmitter yan kasi maliit eh. And then right in the center is the first amateur radio satellite in space. We call it Oscar. Right? Orbiting radio communication in amateur radio, Oscar. And at that time, you still need a sophisticated equipment to receive that, okay, and transmit into it. Now, ngayon, nandito na tayo sa 21st century. May CubeSats na. Even the Philippines have a CubeSat that's coming up pretty soon, Maya 1. Merong amateur radio transponder yon. Even Diwata 2 will have an amateur radio component. So even with a handheld and maybe even a non-sophisticated antenna, you should be able to talk or receive when the satellite is above for at least 10 minutes. Yun ang magkagandahan ng ano. And yun lang equipment na kailangan mo. Look at that guy. May antenna ganyan, hawak-hawak. Tapos naka-handheld lang siya. And he's talking to anybody within that footprint. Yun ang kagandahan ng amateur radio using AMSAT or amateur satellites. So, now how do I do this? Can I play this thing? Tawag nito? The video. Is there a way I could do that here? Okay. You are listening to the Sputnik satellite. Play it, please. Anyways, pag natin narinig, okay. That was received only, and there was several stations down Earth that was receiving that. Okay. One of them happened to be one of my friends, an older friend of mine, that in 1958 yata received this signal on his shortwave radio. Okay, can you play it? The reason why I want you to play is because it was so archaic. All you heard was the tone of the satellite. Okay, hindi bale na. Anyways, let's move on. Here's another one. If we could play this thing, it would be nice. It's using that Oscar satellite that you guys saw earlier. This was supposed to be a conversation between an Italian station with a French station. And what I was going to show you guys was the frequency, the one in the red. If you can see, kasi it also looks back at the Sputnik satellite. And pabayaan mo na, let's go back to where I was. The frequency changes from horizon to horizon because of the Doppler effect. Parang may train, pag nasa train station ng ganyan, o MRT, tapos parating yung MRT, the tone of that train differs from when you first heard it until when it came right next to you. Okay, so okay, I can go for that. Okay, now this is the International Space Station. Again, our first attempt was last February. Hindi namin nakausap kasi madaming interference sa Metro Manila area. But in May, we were lucky to be able to talk to them. Ang gusto ko kaya ko papakita yan is because okay, it's because there are several antennas in the International Space Station that amateur radio related. Okay, there is one in the U.S. side of the ISS, and there's one on the Russian side of the ISS. Okay, the Russians sends a lot of data to Earth for students like you to take a look at it. Nasa YouTube yan. They have a website that shows those slow scan TV. Okay. But on the U.S. side, there is also communication between Earth. So what I'm going to do next is I'm going to take 2 or 3 high schools in Manila, and I'm going to put them in the queue so we could speak to the International Space Station sometime at the end of this year or beginning of next year. So I'll be looking for 3 high schools. And then the following, 3-4 months afterwards, I will do that in Cebu, in the Visayas. So you guys have a chance to talk to the space station astronauts. Ano ba? Okay ba yan? Okay. Kung gusto i-volunteer nyo yung school nyo. Sige. Anyways, maski kayo right now, you could go to your laptop, computer, or tablet, and you could go to ISS tracking software or ISS.com. You will be able to track the ISS satellite as it passes through the Philippines. As you can see, that thing was day and night is passing through Africa, and then it will pass through Australia, just missing the Philippines just by several 100 kilometers. So, nasa ano yan? Nasa internet yan. Okay? Here's another one. If we could play this thing, I would love to do it because maririnig nyo yung American astronauts trying to get a hold of us in the Philippines. Kung pwede ba natin ano ito? Pwede mong i-play? So maririnig nyo yung astronaut trying to call us. His call sign was OR4ISS and our call sign sa Philippines was DX1ISS. It looks like it's playing now. Pero wala lang audio. Gusto mo kasi hello, test. Okay. Well, play from the beginning. Kasi I have 15 seconds with the ISS astronaut there. If you can play from... Ano na ito? Towards the middle na ito eh. Sa beginning. Ayaw talaga tayo ng astronaut. Ayan, sige. Oh, wow. Ganyan kami noong February. We were 15 minutes. He was trying to get a hold of us. I was trying to get a hold of him. Yan. Siya yan. Pinapapunta niya kami sa channel 40. Okay. Anyways, siya yun. He was trying to get a hold of us. And then what I did was I superimposed this other slow scan TV image that the ISS, that cosmonaut was trying to send to us. And as you could see here, nawalan ka ng signal because may mga interference dito. Deliberate interference. Dapat pahuli natin mga yan. So, nanggugulo sila eh. They're there every night. Okay? So, yun ang problema dito. Anyways, how could you do this? Kayo, you could build your own cross-shaggy antenna with a handheld. You could buy one for 1,000 pesos. And then get a tablet. That is a Arduino-based tablet. There are freeware satellite tracking software in the internet. That's all you need. And then I said you could either build the antenna, which we did. We were using discarded television antennas at Holy Angel University. We were able to build one. Again, that's a very simple one that you could do here. When the Diwata 2 comes here, if you have that, you should be able to talk to the Diwata satellite. Okay, and then there are several tracking software, and kagandahan yan, they're all free. Okay, you could go and do this and download them for free para maaralan ninyo. Madali naman gamitin eh. Okay? And then of course, this is, what do you call that? My old satellite ground stations estates. And I have a tablet to track them. I have a antenna rotator system that tracks the satellite and goes from horizon to horizon. And this is at Holy Angel University. We have 2 antennas that we use to track both AMSAT satellites and weather satellites. And we have 3 displays. One is the satellite tracking, the controller of the SDR, software-defined radio, at saka yung image. That's our first image of the Philippines. Or you could be a semi-professional from the University of Florida and have a professional console and a ready to buy antenna system. Okay? And before I go, if you're interested to become an amateur radio operator, you have to attend the Philippine Amateur Radio Association orientation, 2nd Saturday of the month, sa NTC building sa Agham Road. Okay? And that is the only way you will receive what they call a certificate of attendance. you will need that to get your license. Every Wednesday of the week, there is a licensing session sa NTC. You could either get the EC Class D exam, which a grade school student can pass, Class C, which a high school student can pass, or a Class B, which a PRC licensed ECE could easily pass. And then after that, you apply for your amateur radio call sign, and you're legit. You could talk legally on the air. Okay, any questions? Interesado kayo, ha? Para madaming amateurista dito, matulungan nyo yung space program natin. Okay, thank you very much.
So thank you, Engineer Leo, for that wonderful presentation about amateur radio and amateur radio in space. At this portion of our afternoon session, we are going to have an open forum. And if we like your question, we might give you something. So may we call on our speakers to please sit on stage so you can have the children confront you with their questions. And so,
if you guys want to ask questions, there's a microphone in the middle of the room.
yeah. Questions about satellites, the Phil Microsat program, amateur radio to Engineer Leo. The data we gather from Diwata 1 and our subscription satellites. And you might just get this brand new Diwata 2 shirt na pinag-aagawan po ng mga tao. As in, lahat ng pupunta sa baba, wala bang pa-t-shirt yan? Ito na siya. Ito siya. So, if you have a question, just raise your hand. We'll call your attention. Then you can proceed to the mic. Sina.
Yeah, na. Yes. But, okay.
Say, okay. Noted.
My name is Hilton Jan. So my question is, Miss Constante said earlier that satellites such as CubeSats cannot be maintained. Should they fail to function, will be the end of their operation. How can these satellites be retrieved? Because I saw earlier that these tiny satellites have tiny propulsion systems to really make a change in velocity to derail its object. Will they just become a space junk?
Actually, yung mga CubeSats and most satellites naman, kusa silang bumabalik sa Earth. Hinihila sila pababa. So, nagre-re-entry yung mga CubeSats, pero nalulusaw na sila sa atmosphere. And mas masasagot din yata siya nung thermal engineer natin.
Tama yung sinabi ni Mean. So, kusang bumababa yung satellites due to drag. So, may atmospheric drag na tinatawag and hinihila siya pababa nung atmospheric drag pabalik sa atmosphere ng Earth. That's for CubeSats. So, normally, sila yung nire-release sa ISS. So, 400 kilometers yung altitude nila. But for satellites higher than that, yung lifetime kasi, nagbabago yun exponentially depende sa altitude niya in space. So, pag mataas na yung, or malayo na yung satellites from the Earth, humihina yung hatak ng drag, atmospheric drag sa kanya, so tumatagal yung lifetime niya. So what the UN is pushing para mawala yung debris in space or ma-mitigate yung debris in space, ang ginagawa nila is sinasabihan nila ang lahat ng gumagawa ng satellites to put a deorbiting mechanism. So yung deorbiting mechanism, dinedeploy yun pag say, kuwari, sira na yung payloads ko, hindi na ako makapag-take ng pictures, so floating junk siya sa space. So i-deploy yung deorbiting mechanism na yun. So ang mangyayari nun is, it's like a foil, a sail, pwede mo siya i-search sa internet. Ang mangyayari nun, lalaki yung area ng satellite mo. So ibig sabihin nun, tataas rin yung atmospheric drag mo.
Yeah, you're correct. The ISS is an example of a low Earth orbit satellite. Okay, about 400 kilometers lang yan. The reason why they're up there is, right, they have a booster. They'll boost it on their orbital pa. Pag bumabagsak na sila, nakikita na nila babagsak, they'll relit the booster, and so they'll go back to their intended orbit. But without that, like you said, drag, babagsak yung satellite mo.
All right, we like your question, so please claim your prize. Yes, you. Yes.
Yes.
Ay, sige, siya muna. Nauna siya kanina. Yeah.
Good afternoon lang po. Out of curiosity question lang po ulit. Since kanina po, parang yung dinidiscuss po between microsatellites, tapos po yung larger satellites po. Yung difference lang daw po kasi nila, base po sa pagkakaintindi ko, mas prefer yung microsatellites since yun yung mas may cheaper price and parang, ayun nga po, mas mura. Pero kung if ever man po na may sponsor man po na sasagot nung, hindi naman po ako yan, mamaya po, maisipin nyo ako eh. Wala pa po kasi yung pera for now. For now. Pero kung papipiliin po kayo, para po sa inyo, ano po yung mas efficient or mas preferable between the two?
Sige, ma'am.
So, medyo ko-correct ko lang So, una, depende kasi siya kung para saan mo siya gagamitin. So, yung sa sinasabi, siguro yung kanina, may comparison si Mayan regarding sa communications, right? So, in terms of Earth observation, say, environmental monitoring, of course, we would like to have the payloads or the imagers on board a big satellite. Mas gusto namin yon kaysa dun sa microsatellite. But what we have now is a microsatellite. So kung papapiliin kami, syempre mas gusto mo yung mas maganda. Para kang namili sa iPhone 7 at 3210. Not saying na pangit yung Diwata or kumbaga yung 3210 kung ang goal mo ay makapag-text lang. Mas kukunin mo yung mas mura kung yun lang yung pera mo. Pero kung may funding ka at mas malaki yung objective mo na gusto mong gawin, edi why not dun sa mas malaking satellite, right? Yeah.
Wait lang po, Pablo, question lang po. Kasi po may tanong po to. Ano daw po, yung about daw po sa amateur radio daw po, if isa may agham daw po, ano daw po, yung schedule daw po nun, every Wednesday po?
Yung exam, pero kailangan mo muna ng orientation, which is second Saturday of the month. You go up at the NTC building, 4th floor, and sasabihin sa iyo kung nasaan yung orientation. So it's a lot of people, every time I'm there, puno. So you have to schedule that, and you have to be there early, before 8 o'clock. Ang kagandahan ng pag nandun ka, yung certificate mo, bibigay ka agad sa'yo. So, and then you go back, kung tika Metro Manila ka, you go back the Wednesday of the following week, you can take the exam na.
Is July po or next August?
August ka na. Okay?
Thank you po.
All right, thank you. We liked your question, but you had a shirt this morning, so we'll have the next question. Yes, sir.
Good afternoon, I'm Henry. My question is, the advancement of the Philippine Space Development Agency depends on the structural form of government, because the government procurement system requires geopolitical decisions. Now, do we need to change the current form of the government, like the Republic and Democratic? Yes or no? And if your answer is yes, why? Do the federal government is the applicable?
It has nothing to do with the government. Because the number one space agency before 1969 was Russia. That's a communist country. All right? And then the next one was East Germany, another communist country. So it has nothing to do with the government. It has something to do with the people that wants a space agency. Yun lang yun. It's like, which one came first? The chicken or the egg? Anong gusto mo? So, nasa tao yun. And there's, I have 30 years experience on this. Ang pagkakita ko, there is a lot of na magandang ibibigay sa Pilipinas ang space program. Hindi lang sa isang forum talagang sinabi kong ilan yun. May mga rations kami kanina doon. Natutulong sa Pilipinas. Okay? And yun lang yun. It has nothing to do with the government. Basta kung gusto mo, gusto mo.
So you mean your question is remain status quo? No need to federalize?
Doesn't make any difference which one. Like I said, sa Russia, Khrushchev said, I want it, boom, just like that. Kennedy says, I want it, boom, just like that. So the government has nothing to do with it.
Yes, but to add on, I think the current station of the Russia is still the #1 in the whole world. And even in cyberspace, cyber digital technology,
Yeah,
#1.
which one? Who's #1?
The Russia, the Kaspersky Law.
I beg to differ because, like I said, I work at the Space and Naval Warfare Center of the United States Defense Department, and we do not advertise what we do. And I pretty much guarantee you that we are in par or even greater than the Soviet Union.
But I want to enroll you in the amateur radio.
Well, whatever.
Yeah.
So,
Thank you.
no problem. And just to emphasize this thing with your question, when I was a SPAWAR, what we did was we have CubeSat that we deploy, cost $1 million, because we could not afford to burn $140 million budget just to experiment in space and then sira. So that is the difference. Okay, you spend $1 million for a specific experiment, or you want to spend $140 million for a specific experiment. I would rather pick the $1 million, right?
Yeah.
Okay, thank you.
Another question, do you think that the Space Museum in the future would be feasible? Because I'm also advocate of the United Nations World Tourism Organization. Like the Jank, the Sputnik, it's good museum piece.
Yeah, you could make your own replica of those first satellites, and yeah, you could, with the space, your national space program, you should be able to do that, and it'll be a good, like you said, a good tourism project. Okay.
Thank you.
Anybody else?
All right, thank you. Next question. Yes, this guy from front. Yes.
Good afternoon po. I'm Jafet po from PUP po. So, I have 3 major questions po from Diwata.
Pick
Kasi
one.
Po, kanina po sa exhibit, naging interested po kami. So, yung first question po is, from Diwata 1 and Diwata 2 po. Ano po yung pinakamalaking difference po ng Diwata 1 between Diwata 2? And yung second po is, ano po yung upgrade or advanced features of Diwata 2 than Diwata 1? And last po, nalaman po namin na kaya po na-create po yung Diwata 2 kasi po nasisira na po yung Diwata 1. And the last question is how long po yung lifespan po ng Diwata 2 or gaano po siya tatagal?
Kaya bang isang sweep na...
Dami, nakalimutan ko na. So yung first difference, main difference would be si Diwata 1 released from ISS. Diwata 2 will be piggyback sa isang malaking H2A rocket. So yung altitude ni Diwata 2 is higher than Diwata 1. So mainly ang impact nun is it will have a different orbit. So it will have a Sunsynchronous orbit. So it will enable us to monitor, mas nape-predict na namin yung, or it will, yung revisit interval ni Diwata, mas predictable na, therefore mas makakapag-monitor na tayo. That's one. Tapos ano yung
Yung 2 po is, ano po, yung what are the upgraded features or advanced
Ayun,
features
yun,
of the
well, medyo upgrade naman yun. Ay, hindi, malaking upgrade yun.
sa material?
So in terms of the cameras, madadagdagan siya ng isa pang camera. It's called Enhanced Resolution Camera. So, ang gusto namin gamitin yung camera na yun, well, that is a panchromatic camera. We want to use it to pan-sharpen the images of SMI. So that's one. And then the lifespan of Diwata. Oh.
For Diwata 2, ang projected is 5 to 10 years yung lifetime. For the orbit, it might change, vary depending on the, like I said, yung value ng atmospheric drag during or while it's in orbit. So yun yung mainly nagde-dictate kung gaano siya katagal in space. But normally payloads last 4 or 5 years, mga ganun. So I think we have a mechanism in place naman to deorbit it once it's already a junk in space. So yun. For the upgrades, we have the amateur radio, like Sir Leo mentioned. We can talk to other ham radio operators in other areas in the Philippines that doesn't have, or pag down yung telcos, we can rely to that system. We have added a attitude control unit, experimental attitude control unit. It's also done here in UP Diliman. Ang use niya is to refine the pointing accuracy of the Diwata 2. So kasi like Miko mentioned, yung satellite is moving 7.2 kilometers per second. And that's very fast. And one or a point something degree of error would mean or would translate a bigger or a very big error in the ground. Say pag 0.1, I'm just throwing numbers. So kuwari 0.01 degree yung error na yun, it might translate to say 40 kilometers in the ground. So we would like to reduce that error. So ano lang yun, numbers lang yun. I'm not calculating right now. So maybe it will change. Also, we added a sun aspect sensor. It will calculate the orientation, the current orientation of the satellite. So it will help feed on the attitude control unit as well.
Thank you po, sir.
All right, next question. Oh my gosh.
No
ang
more
daming tao.
3-in-1 questions, ha? One question lang.
The guy in blue.
Curious lang po, what are the countermeasures being done to protect or ensure the data of the water, the satellite, na pinapadala, or the satellite itself from being hijacked or hacked?
Anyone?
Yung data na pinapadala, hindi naman siya pinapadala as is. May mga encryption siya, tsaka encoding na ginagawa. So actually, kahit itry mong i-snip yung mga data na nare-receive from satellites, hindi mo rin siya ma-decode or ma-decrypt.
Unless alam mo yung sync code.
Also, the sophistication is now, we use what we call low probability of intercept. We bury the signal in the noise. Unless you have the sync code, you won't be able to sync with the data that's being transmitted, because it's what they call multi-phase keying. Okay, if wala kang correct decoder sa baba, you cannot be able to do that. So, but in the future, there will be what we call frequency hopping and low probability of intercept. So there's no way you could intercept any signal unless you have that sync code.
Thank you, sir, for that answer, and ma'am.
Guy in glasses in gray. Please limit your questions to one.
No follow-ups na, ha?
So my question is that can cube satellites or microsatellites actually go farther than low Earth orbit?
It's a good question.
Actually, in most cases, you can launch a satellite kahit saang orbit mo siya gusto. Pero kasi, for example, magsasakay ako sa rocket na worth 6 billion pesos nung isang 1U CubeSat. Baka hindi nagbe-make sense. So, you usually place, kumbaga, tinatama mo rin yung size niya sa kung saan siya mag-ooperate. Kasi yun nga, mahal yung launch cost. So, if it's only a 1U CubeSat, you will normally deploy that on a low Earth orbit.
And there's also an organization called ITU, International Telecommunications Union. You register your satellite orbit. Okay? Pag na-register mo na yan, hindi mo na mapapalitan yan. So, there's no way you could reorbit the satellite maski may booster ka. Eh kung merong another satellite that's above you, titinamaan mo siya.
Also, I'd like to add, normally when you go outer space, there's a complicated science happening. So it's not just like, oh, I'll go to Mars, parang ganun. Ang nangyayari kasi niyan, normally pinapadala sa isang parking orbit kung saan siya magpa-park. I think mas maintindihan or mas okay if manonood kayo ng The Martian na movie. Ayun. So, may parking orbit yon, and then pag naabot niya yung certain point at that orbit, kailangan niya mag-release or mag-boost para lumipat siya ng another orbit, which is yun yung papuntang Mars. So as yung tanong mo kasi is on CubeSats and microsats, so you need to put boosters, thrusters, so mag-occupy siya ng weight. So medyo, I think, sayang if ipapadala mo siya to outer space. So just use it for science na lang.
Actually po, I also had this very question po kanina regarding the tests in satellites po. Is the testing for satellites only for common astronomical phenomena, or do you also consider the uncommon astronomical anomalies inside the solar system?
For example, do you have an example in mind?
Actually po, there is this one example that I've been having in mind po. For example, the solar bursts po, which is the sudden explosion of sunspots releasing deadly electromagnetic waves po.
So I think pinakita ko kanina we're doing radiation testing. So I think that covers the burst of solar flares that you are mentioning. So we expose the electronics of components of satellites to intense radiation and see if the components fail or not. So pag nag-single event upset ba or may single event effect.
Also, do you know that there is an 11-year solar cycle in your study? We are at the minimum right now. So your solar index, especially the K index, are very, very low. There's only a few solar bursts. But once we go down, it goes fast, very exponentially. Doon mo makikita yung mga solar flares because the sunspot numbers are humongous. Okay, and sometimes it is so humongous, it blanks out the electromagnetic waves that are trying to come in or go out. So everything is based on the 11-year sunspot cycle, solar cycle.
Just to add dun sa sinabi nila, actually marami ka talagang i-consider kapag mag-launch ka ng satellites to space, hindi lang yung sa solar flares na sinasabi mo. In terms of radiation, maraming sources yon, which is yung sa sun activities, nandyan din yung galactic cosmic rays, tapos yung Van Allen belts. Tapos other than that, you would also need to consider yung mga debris na pwedeng bumangga sa satellite mo kasi they're all moving at a very high speed. Tapos, in terms of yung effects naman ng vacuum, nandyan din yung cold welding and then meron ding atomic oxygen. So maraming factors na kailangan i-consider and you need to basically study all those to be in developing and testing a satellite.
All right. We only have time for 3 more questions, so make it good.
Pili ako. Okay lang. Kasi, ikaw na lang.
Zagay, I'm pointing at you. Since nasa isang table kayo, feeling ko, You could just give one question.
One
Faster,
question
faster,
for
faster,
the
faster.
group. Going once.
Come on.
Going twice.
Come on, make me proud, please.
Good afternoon. This question is addressed to Mr. Delbert Michał. If we hypothetically wanted to create a cube satellite, what components are needed to complete a framework for such a satellite?
Kung nakinig kayo sa presentation ko, there are 7 basic parts ng satellite. So, yung 6 lang yung kailangan mo when building a CubeSat. So, you have the bus, so the electromechanical structure that holds everything in place. You have the power source, yung batteries mo and the solar cells. The next one is the communication system. So how would you communicate or how would you send data or download the data from your CubeSat? Next is yung computing system. So paano execute yung commands. And then the next one, the heat control system. And I think that's it.
I think po yung sinasabi po sa question na inaano ng
Okay.
members ko, yung sa tingin ko po yung
Anong
materials.
kailangan nyo? Okay. So for the materials, here, unfortunately here in the Philippines, we don't have those materials yet, or we don't build those materials yet. So what we, or the team usually does is we buy some components off the shelf from other countries, from abroad. But we're trying to develop a CAN satellite. We use it for technology demonstration in the university. And what we use are yun, COTS pa din, commercial off the shelf, pero you can buy it here locally. Pero if you want to say bring that satellite to space, then I think you should buy components first from abroad and integrate, assemble it here. And another thing, normally yung structure kasi ano siya made of aluminum alloy, so you need a CNC machine and all those machines to cut those parts. And PCBs, maraming PCBs ang CubeSats. So mostly PCBs yun. Solar cells, mahal na solar cells. The high efficiency solar cells, normally triple junction na solar cells para high efficiency, mga around 28%. And ano pa ba? Batteries, you can choose from lithium ion to nickel metal hydride to nickel cadmium. So nagde-differ lang siya sa operating temperature ranges ng batteries na yon and the discharge cycles. So I think that's it.
All right, Jervic, can you pick the next question?
I think kailangan maglabas ng user manual for Diwata 2 para aralin niyo na lang. Sir, with the glasses, yes po. Basta one question.
Sir, kasi po dati yung Space Shuttle Orbiter po yung nagpa-perform ng burns para po ma-raise yung altitude ng ISS to maintain its orbit. Pero nung na-decommission po ito ng 2011, ano po yung ginagamit po ngayon ng ISS para po ma-maintain yung orbit niya po?
You mean the ISS itself? Kung anong yung ginagamit nila?
Para po ma-maintain yung orbit po nila.
It's a combination of may silang mga ion thrusters, because this was designed way back 10, 15 years ago, and still it's the same thing. They use ions to ion thrusters and boosters to do it. Yun ba yung question mo? Yeah. Okay.
All right.
One last question.
You. Ikaw. Next to the guy in blue. And you're also in blue.
Yung question ko po is, as a whole team po ng Diwata, do you think that Diwata 2 would be a total upgrade from Diwata 1? And if not po, what would it, ano po yung features po na malalak niya? And there's a chance po ba for a Diwata 2?
Ay, wow, so may upgrade kasi pa +1 dun sa number. Pero sige, let's have the team answer it. Do you think it's a major upgrade? mga features na nilalak pa nung Diwata 2? And is there a chance for a Diwata 3? Tatlo yun na.
Oo nga, dami. Dapat isa lang eh. Hindi ko na naabutan yun sa baba. So as we've answered earlier, there are a lot of difference no between Diwata 1 and Diwata 2. So sa tanong mo kung upgrade ba siya? Oo, definitely. Since Diwata 1, wala pa kaming alam. When we started Diwata, well, medyo may, pero wala. Nung Diwata 1, I mean, wala pang nagagawang Diwata, for sure. That's for one. So nung Diwata 2, we experience a lot of things from Diwata 1. So may knowledge na tayong nakuha from Diwata 1, and we apply that in doing or in developing Diwata 2. That's one. Tapos ano pa yung, kung meron bang Diwata 3? Teka lang, naghihanap ako ng project leader dito eh. May nakita ko kanina kaso wala. So, baka meron, pero baka hindi na Diwata, no? Or iba na yung pangalan niya.
Anito.
Kung magkakaroon ng Diwata 3, siguro depende sa government. Hindi rin namin masabi directly.
Yeah, for Diwata 3, so for Diwata 3, yun, kagaya na sinabi nila, it's not sure. It would mainly depend on the government if they give funds for building Diwata 3 or not. But we're planning to, like Dr. Marciano mentioned in his presentation, we're planning to build a local industry base. And we're trying to proliferate the knowledge that we've gained while we were in Japan, and try to proliferate it to students like you guys. Or I think we're planning to offer graduate studies in UP. We're going to invite other faculties from different universities around the Philippines and start teaching them satellite development and the whole process.
All right.
So I guess that about that
Fine. One last question and make it good. Guy with the curly hair.
Hello po, ako si Gian from UPLB Applied Physics. So, tanong ko lang if ano yung mga methods or procedures para i-analyze yung images na na-obtain gamit si Diwata and gaano siya katagal?
Gusto ko. Oo naman, sumagot ka naman.
Sumagot na ako kanina eh. Pero okay. Anong mga methods ang ginagamit para nakakatakot andyan yung boss ko? Sige, mag-cite lang ako examples. So, ano mga ginagawa namin na methods? So, una, kung nakita niyo yung ibang images na pinakita ni Kay kanina, nagpakita siya ng mga classification maps. So one, we're doing image classification. So that means we're identifying what type of surfaces we're seeing in the images. So kung forest ba to, agricultural land ba to, water body ba to. And then, tama ba? Ganun bang klaseng process yung hinahanap ko?
Gusto ko sana yung specific na procedure.
Algorithm. Mag-uusap tayo mamaya. Sige, mahaba-habang kwentuhan yan. And then yung isa mo pang question is, gaano siya katagal? Okay, so from the moment na nag-upload tayo ng commands, so nakuha natin yung images, it can take at fastest, I would say, is about 2 days. Yun yung optimal conditions, like nothing goes wrong. And then, in terms of processing the images, marami siya pinagdadaanan na steps eh. So the first step is actually called georeferencing. So once we download the image, we don't know where the image is in the map. So we have to locate it and then tag the points. Tag the points para lumabas siya sa map. Then that usually takes about mga 3 hours siguro. Fastest is 3 hours. And then pag okay na yun, meron naman kami mga codes for processing na you just run it. It should take only about a few minutes. So fastest is 3 days. Pero that's super optimal, I guess. Pero realistically, we're doing it about a month kasi sobrang daming images na kailangan i-download. Sometimes when we download the images, maraming data loss and we still have to complete those. And then sometimes we're having trouble finding where the images are exactly in the map. So maraming kailangan i-consider na factors. Ayun.
Thank you.
So, okay, yan, sir.
No, I mean kasi my team is sila Miko sa analysis, but before that may pre-processing pang nagaganap. So yung sabi ni Miko yun sa georeferencing, we're actually trying to work with that kasi medyo tedious siya. Like sabi ni Miko, 3 hours. Like right now, na-reduce namin siya to around 30 minutes and we're working on automating it. Kasi ngayon, tao pa yung tumitingin, hahanapin mo yung image, tapos assign mo yung coordinates niya. So right now, yung goal namin ay full automation. So pag may image, GGRF na siya. So that should take like seconds. Pero right now kasi medyo mahirap pa siya. So yung ginagawa namin, semi-automation. So di ba nakita niyo kay Miko, maraming images yun, isang track siya, di ba? Maraming images na sequential. So right now, yung ginagawa namin, pag nakakuha ka ng isa doon, kaya mo nang i-stitch yung iba. So image matching siya. So yun, tsaka other automation.
So we would like to thank everyone in the audience who asked. And if you have more questions, you can email us at info@asti.dost.gov.ph. That's info@asti.dost.gov.ph. And of course, we would like to thank our speakers for the valuable knowledge and interest, and I guess newly struck passion in our youths present in the audience about space and the future of our space program. So let us give our speakers a very, very big abot sa space round of applause.
And to formally close this afternoon's symposium, we would like to welcome the project leader of the Phil Microsat Project 1 or the Bus Development Team to give us the closing remarks and to give the certificates of appreciation for our speakers. May we please welcome Dr. Mark Cesar Talambas.
Good afternoon, everyone. Akala ko tapos na kasi nagpalakpakan na kayo eh. So to formally close this event, thank you very much for attending at for asking very interesting questions to ating mga speakers. And of course, pasalamatan uli natin sila for sharing their knowledge and experiences. So nagsimula tayo dun sa intro ng satellite technologies, napunta sa space environment, ano ba yung kailangan na i-survive ng mga satellites natin, pagdating sa nanosatellites and CubeSatellites. Pinag-usapan din kanina kung ano yung mission ng Diwata, paano siya ino-operate, ano yung process ng pag-acquire ng images. Parang may discussion pa nga kayo na RGB. I think iba nga sa atin, hindi alam yan, ganun pala yung composition ng images, di ba? Yung pixel, picture element pala. Di ba? So marami tayong natutunan ngayon and baka nga info overload din eh. So it may take some time na i-process natin talaga yan, no? And of course, narinig din natin yung talk ni Dr. Joel Marciano. Always a pleasure to listen to that guy. Parang every time magsalita siya, no, may bago ako na pick up. Kahit yung presentation niya kanina, alam ko nakita ko na yung before eh. Pero every time pinapakita niya yun, laging may bagong nasasabi. So after nun, si Sir Leo, of course, shinare yung tungkol sa amateur radio. And in-invite kayo to, of course, get your license and volunteer yung organizations and schools nyo to have their own amateur radio and satellite stations. May question pala ako, Sir Leo. Hindi ko alam kung natanong, may age limit po ba? Or may minimum age na kailangan dun sa pag-apply ng license?
They changed it from 12 to, I believe, 10.
Okay. So, sinong pinakabata dito? Meron bang 10-year-old dito? 11? 12? 13? So, si Gladys daw ay 10 years old. Okay. Pero may license ka na, di ba? So, nagbibigay nga sila sa 10-year-old. Okay. So, yun po. Kung interested kayo to become a licensed amateur radio enthusiast, nakita nyo naman kung ano yung process kanina. No? And finally, yun nga, nagkaroon tayong question and answer. Daming tanong. Di ko alam kung interested ba talaga sa space or sa t-shirt, pero hindi nagmamatter yun. Okay? And yun, so thank you very much sa inyo for being a very good audience. And pasalamatan din natin ang DOST-ASTI and DOST in particular sa pag-hold ng event na ito. So maraming salamat po. Ano ba yung ko?
So, Sir Mark will be giving the certificates of appreciation to the speakers for the invaluable sharing of knowledge and expertise as resource speakers for the Philippine Showcase of Space Technology during the National Science and Technology Week 2018. So, he will be giving the certificates to Mr. Romer Christy Aranas, RK Aranas, Delbert Schmidt-Chow,
So, sana ang takeaway nyo from the National Science and Technology Week and lalo the new face of data science in the Philippines and, you know, yeah, and